Hello there, and welcome to Science for Sleep, where curiosity drifts softly beside you and science takes the long, quiet road towards slumber. Tonight, we're setting our sights on something both impossibly large and strangely comforting. The question of what lies beyond the expanding universe. It sounds grand, doesn't it? Almost too big to hold in the mind at once. And yet, here we are, just you and I, lying under the same stars, wondering together about the edges of everything. Before we start, I'd love to know where you're listening from this evening. Are you curled up in bed, letting the hum of the day fade away? Or perhaps you're somewhere on a couch with the glow of a lamp nearby. Maybe you're in a different corner of the world altogether, where it's morning instead of night, and the thought of drifting into sleep feels far away. However you arrived here, you've brought your own little pocket of the universe into this moment. If you find comfort in these gentle explorations, I'd be deeply grateful if you tapped the like button, or even subscribed. It helps this calm little corner of science reach others who might also need a soft landing at the end of a long day. So now let's begin our journey. The universe is expanding. That's not a metaphor or a bit of poetic exaggeration. It's a literal fact discovered by astronomers nearly a century ago, and it means that everything we see in the night sky, the galaxies, the clusters of stars, even the very fabric of space, is stretching. Not racing outward into empty space the way fireworks scatter into the sky, but rather space itself is growing. Imagine the surface of a balloon with little dots drawn on it. As the balloon inflates, the dots all move away from one another. None of them are at the centre of expansion, and yet all of them feel the stretch. That's the reality we live in. Though our balloon is four-dimensional, and we're stuck on its surface watching the distances grow. When we say the universe is expanding, it immediately raises the question that lingers in the mind like a stubborn whisper. Expanding into what? If space is stretching, what is it stretching into? If there is an edge, what lies beyond it? These are not easy questions, and for most of human history they weren't even thinkable. For centuries people saw the sky as a dome above the earth, something that wrapped around us like the roof of a house. The stars were fixed lights, and the universe felt finite and local. Only in the last 100 years have we come to grips with the idea that we live inside something vast, ancient, and still in motion. That realization alone is enough to make the heart beat a little quicker, even as you're trying to let the day's worries slow down. One of the curious things about the universe is that it resists being put neatly into the boxes we want to make for it. When you try to imagine an edge, your mind immediately supplies a wall, a barrier, something with a beyond. That's how our everyday world works. The room has walls, the book has a last page, the day has a sunset, but the universe, as far as we can tell, isn't built to fit that pattern. If space itself is all there is, then asking what lies outside is like asking what's north of the North Pole. It's a question that makes sense in language, but perhaps not in physics. Still, it's exactly those questions, the ones that wobble at the border between sense and nonsense, that drive us forward. Imagine yourself lying on your back under the night sky gazing upward. The stars look scattered, but in truth they form part of enormous galaxies, each containing billions of suns. Beyond those galaxies are clusters, and beyond those, vast filaments of matter stretching across unimaginable distances. The scale is so enormous that even light, moving at its staggering speed of nearly 300,000 kilometers per second, takes billions of years to cross it. And yet, the expansion of the universe means that much of what you see in the sky is already different by the time its light reaches your eyes. The Andromeda Galaxy, for instance, appears as a smudge in the northern sky. What you see tonight is what it looked like more than 2 million years ago. When your ancestors were barely discovering fire, the light that is now striking your retina was just beginning its journey across space. And that's the nearby stuff. The more distant galaxies we observe, the farther back in time we are looking. At the farthest limits of our vision, we glimpse the faint glow of the cosmic microwave background, the leftover heat from the Big Bang itself, stretched thin and cooled by nearly 14 billion years of expansion. Beyond that veil, the universe becomes opaque to our instruments, a curtain we cannot see through. So already, in a very real sense, there is a beyond to our universe, though it's not an edge in space but an edge in time. Beyond that curtain lies the moment when light itself first had room to travel, when the universe cooled enough for atoms to form. What lies beyond that moment is hidden not by distance, but by physics itself. Still, even that explanation doesn't satisfy the wondering heart. If space is expanding, is there an outside? If galaxies are moving away from us in all directions, where are they going? These are questions that physicists wrestle with, and the answers are subtle. In most models, the universe doesn't expand into something else. Instead, the expansion is the increase of distance between objects within the universe itself. There is no outside, just more inside, more space stretching, more room appearing where there was none before. That idea can feel strange, but then again, so can most of modern physics. Think about a horizon. When you stand at the shore and look out to sea, the horizon looks like an edge, a boundary where the ocean ends and the sky begins. But if you travel to that horizon, it moves with you. There was never a literal edge, only the limit of what you could see from your spot. The universe works a bit like that. The cosmic horizon isn't the end of everything. It's just the limit of what we can observe. Beyond it, the expansion of space is carrying galaxies away from us so quickly that their light will never reach us, no matter how long we wait. They vanish beyond the curtain of visibility, not because they've stopped existing, but because the universe is stretching faster than light can carry their story to us. As we sit with that image, the mind drifts again to the question of what it means to live in a universe with no edge. If there is no boundary, then perhaps the universe is infinite, stretching without end in all directions. Or perhaps it is finite but unbounded, like the surface of a sphere. You can travel forever without finding an edge, looping around endlessly, always discovering new sights but never encountering a wall. Both possibilities are dizzying, and both are still open in the science of cosmology. Measurements of the universe's curvature suggest it is remarkably flat, which could mean infinite or could mean so vast that any curvature is too small for us to detect. All of this might sound like a lot to think about as you're trying to let your eyes grow heavy. But there's something deeply soothing in the scale of it too. The worries of today shrink a little when set beside galaxies rushing away across billions of light years. The deadlines, the traffic jams, the unanswered messages, all of them exist inside a universe that is not just large, but still becoming larger every moment. It doesn't make those things vanish, but it sets them in a frame so wide that even worry itself begins to soften at the edges. And so, as you listen now, think of the expanding universe not as something that excludes you, but as something you are part of. Every atom in your body was once compressed into that tiny hot seed of the cosmos before expansion began. You're not outside looking in, you're inside looking around. And whatever lies beyond, whether it's more of the same or something altogether unimaginable, you carry within you a piece of its story. The starlight that reaches your eyes tonight has crossed billions of years to meet you, and you in turn are made of the same stardust that lit its way. From here, we'll wander deeper into this story, into the discoveries that revealed expansion, the strange energy that drives it, and the horizons that set the limits of what we can ever know. But for now, simply rest in the thought that the universe is moving, quietly, steadily, carrying galaxies apart and drawing us into the question of what lies beyond. The journey has only just begun. The universe is never still, even on nights when the sky appears perfectly calm, when the stars seem pinned like jewels on velvet. Everything above you is in motion. Our planet itself is spinning once every 24 hours, carrying you from sunlight into night and back again. The Earth also circles the Sun in a yearly path, and the Sun in turn is drifting around the centre of the Milky Way, a slow orbit that takes more than 200 million years to complete. Yet even these grand motions are small compared to the greater stage. The Milky Way itself is sliding through space, pulled by gravity toward neighbouring clusters of galaxies, and all the while the fabric of space is expanding beneath it all. To look up is to gaze into a vast dance that began billions of years ago and shows no sign of stopping. What makes this especially curious is that for most of human history, the sky did not look like it was in motion at all. To the ancient eye, the stars were eternal, fixed in their patterns. The constellations rose and set predictably, the sun crossed the heavens in a reliable arc, and the moon cycled through its phases like a faithful companion. Everything seemed orderly and repeatable, a cosmic clock with gears that never changed. Even when astronomers like Copernicus and Galileo suggested that the Earth itself was moving, it felt impossible to grasp. After all, you don't feel the spin of the Earth, and you don't sense the sweep of its orbit. The motion of the universe hides in plain sight, disguised by its sheer scale. It wasn't until the 20th century that scientists began to notice a stranger kind of motion. Not the turning of planets or the swirl of galaxies, but the stretching of space itself. When astronomers first pointed powerful telescopes toward distant galaxies, they expected to see stars much like our own, perhaps arranged in unfamiliar shapes. What they did not expect was that nearly all of those galaxies were receding from us. Their light shifted toward the red end of the spectrum. This red shift was a clue that the universe itself was not static but expanding. Instead of a sky that held steady forever, we live in a cosmos that grows larger with time. To understand this, imagine a loaf of raisin bread rising in the oven. Each raisin represents a galaxy. As the dough expands, the raisins move away from one another, not because they're travelling through the dough, but because the dough itself is stretching. Every raisin sees all the others receding, and no single raisin is at the centre. That's the situation we find ourselves in. From our vantage point on Earth, every galaxy beyond our local neighbourhood appears to be moving away, and the farther they are, the faster they recede. This simple but profound observation changed cosmology forever. What makes the universe's motion even more remarkable is that it seems to have no end point. The galaxies aren't moving away to some empty region where they'll eventually stop. The space between them keeps growing, and as far as we know, it always will. There's no central hub where the expansion began, no outer shell it's moving into. Instead, the whole of space is stretching everywhere at once, a motion so complete that it resists the usual way we think about direction. When you walk across a room, you go from one side to another. When the universe expands, there is no other side. There is only more universe, unrolling beneath its own laws. On the larger scales we can observe the pattern of this motion is astonishingly smooth. Galaxies cluster into filaments and walls that stretch for hundreds of millions of light years. But beyond those patterns lies an even distribution, a kind of cosmic uniformity. No matter which way you look, the expansion appears the same. This principle, known as isotropy, tells us that the universe doesn't privilege any one direction or location. It's expanding everywhere in the same way, and so the story of motion is one we all share equally. Whether you are in a spiral galaxy like our Milky Way, or a giant elliptical far across the void, the expansion looks the same. Of course, not all motion is outward. Gravity, with its quiet but persistent pull, binds stars into galaxies and galaxies into clusters. Within these smaller scales, the expansion of the universe is overcome by the tug of matter. That's why the Milky Way and Andromeda are on a slow collision course, set to merge billions of years from now. While space itself stretches, local groups remain gravitationally bound, swirling around one another in their own smaller dances. The universe in motion is therefore not a simple, uniform stretching, but a layered story. Expansion on the grand scale, gravity on the local, each working together to shape the cosmos. One of the most subtle aspects of this motion is that it can't be felt directly. You and I don't notice space growing between us because the effect is infinitesimal on small scales. Atoms, people, even entire solar systems are held together by forces stronger than cosmic expansion. The motion reveals itself only when you look across vast distances, when light from remote galaxies carries the signature of redshift, or when the pattern of the cosmic microwave background shows the imprint of a universe still moving from its earliest moments. In that sense, the universe in motion is like a silent background hum, too deep to hear directly but evident in the way everything is arranged. Consider the journey of a single photon of light. Released from a distant star billions of years ago, it races across the void at the fastest speed possible, and yet as it travels, the expansion of space stretches its wavelength, turning it redder and dimmer. By the time it reaches our telescopes, it carries not just the story of the star that created it, but the memory of the universe's motion along the way. Every beam of starlight is a messenger from the past, bent and stretched by the cosmic expansion it crossed. To observe the universe is therefore to read the record of its motion written in the language of light. When astronomers map galaxies and measure their distances, they find a simple rule. The farther away a galaxy is, the faster it appears to recede. This relationship, known as Hubble's law, is one of the clearest signs of the universe in motion. It tells us not only that space is stretching, but that it has been doing so since the very beginning. If you reverse the film of expansion in your mind, galaxies come closer and closer together until they merge into a single, dense state, the hot origin we call the Big Bang. The motion of the universe today is the continuation of that ancient unfolding, a process nearly 14 billion years in the making. What lies ahead is even more intriguing. The expansion isn't slowing down as once expected. In the late 20th century, astronomers discovered that the pace of expansion is actually accelerating. Something unknown, dubbed dark energy, seems to be pushing the cosmos apart with increasing speed. This adds another layer to the story of motion. Not only is the universe expanding, it's doing so faster and faster, a restless growth with no clear end. If this continues, galaxies will drift beyond our sight, the night sky will grow emptier, and the observable universe will shrink around us even as the whole continues to grow. The motion of the universe is not just steady but accelerating, and that raises profound questions about what kind of cosmos we truly inhabit. And yet, in the middle of this immense unfolding, life goes on here on Earth at its familiar pace. We measure time in hours and days, not billions of years. We walk across streets, not across clusters of galaxies. The motions that shape the universe are too grand to touch us directly, and yet they form the stage on which everything plays out. Every moment you live is carried along by that expansion. Every breath is part of a cosmos that refuses to stand still. In a way, your very existence is a participant in that larger story. You're not separate from the universe in motion. You're one of its moving parts. As you rest and let your thoughts settle, picture the galaxies sliding away across the fabric of space. Picture the silent stretch that has been underway since long before there was Earth, or stars, or anything we would recognize as familiar. Their motion continues now in the background of your life, steady and certain. When people first turned their telescopes toward the heavens in the 17th and 18th centuries, they saw a sky filled with points of light that resolved into stars, clusters, and fuzzy patches. Those faint smudges puzzled observers for centuries. Were they simply clouds of gas within our own Milky Way, or were they separate island universes of their own? For a long time, the prevailing belief was that the Milky Way contained everything. The idea of countless other galaxies lying far beyond our own seemed almost too extravagant. but astronomy is a discipline that grows with each improvement in vision. And as instruments grew sharper, the story of those smudges slowly began to change. By the early 20th century, a young astronomer named Edwin Hubble was working with the most powerful telescope in the world, the 100-inch Hooker telescope at Mount Wilson Observatory in California. Night after night, Hubble trained this enormous instrument on the faint patches of light known as nebulae. What he saw would overturn humanity's understanding of the cosmos. Within those hazy spirals, Hubble was able to detect individual stars. Among them were a particular kind known as Cepheid variables, stars that brighten and dim in regular cycles. The period of their pulsing is directly related to their intrinsic brightness, which makes them excellent cosmic yardsticks. By comparing how bright these stars appeared to how bright they truly were, Hubble could calculate their distance. The results were shocking. These stars were far too distant to belong to the Milky Way. The nebulae they lived in were not nearby clouds, but vast galaxies in their own right, each containing billions of stars. What people had once thought was the whole universe was only a single galaxy among many. The universe suddenly became far larger, far stranger, and far more humbling. But Hubble's revelations did not stop there. As he continued his observations, Hubble began to notice a pattern. The light from these galaxies was shifted toward the red end of the spectrum. This redshift was a phenomenon already familiar to physicists. When a source of light moves away from you, its waves are stretched, increasing their wavelength and making the light appear redder. It is the same principle as the Doppler effect you hear when an ambulance passes by. The pitch of the siren drops as the vehicle moves away. In light, the effect is seen as a shift in colour. The fact that galaxies showed this redshift meant that they were receding from us. The deeper Hubble looked, the stronger the effect became. Distant galaxies were more redshifted than nearby ones. By plotting the data, Hubble discovered a linear relationship. The farther away a galaxy was, the faster it appeared to be moving away. This became known as Hubble's law, and it revealed something astonishing. The universe was not static as scientists and philosophers had long assumed. It was expanding. This discovery was not entirely out of the blue. In fact, years earlier, Albert Einstein had considered a universe in motion when he was developing his equations of general relativity. The mathematics suggested that space itself could expand or contract, but Einstein found the idea so strange that he altered his equations to force a static solution, introducing a cosmological constant to balance things out. When Hubble's observations showed the expansion was real, Einstein reportedly called his earlier modification the greatest blunder of his life. The expansion of the universe meant that everything we see today was once closer together. If you reverse the cosmic movie in your mind, galaxies that are now billions of light years apart come together into a denser and denser state. That line of thinking eventually led to the theory of the Big Bang, the idea that the universe began from an incredibly hot, dense point and has been expanding ever since. Though the term Big Bang was first coined as a kind of joke by a skeptical astronomer, it stuck, and it remains the most widely accepted description of our cosmic origins. But the discovery of expansion also raised new questions. If all galaxies appear to be moving away from us, does that put us at the centre of the universe? The answer is no. Expansion is not like an explosion where fragments fly outward from a single point. Instead, it is the stretching of space itself. Every observer, no matter where they are, sees other galaxies receding. If you lived in a galaxy billions of light years away, you would observe the same pattern we do. The expansion looks the same from every vantage point. There is no privileged centre, no edge from which everything began. The universe grows everywhere at once. It's worth pausing to imagine what it must have been like in the 1920s and 1930s as these ideas took hold. For centuries, people had believed the stars were fixed in a firmament. Then they learned that the Earth was not the centre, but orbited the Sun. Later, they discovered that the Sun was just one star among billions in a galaxy. And now, Hubble's work revealed that our galaxy itself was only one among billions more, all rushing away in a grand expansion. Each shift pushed humanity further from the centre of things, and each shift expanded our view of what the universe could be. Hubble's law remains one of the most profound insights in science, but it is also deceptively simple. At its heart is just a plot of velocity against distance, a straight line that shows the universe's motion. Yet from that line flows an entire new vision of reality. It tells us that the universe has a history, that it changes with time, and that it will continue changing long after we are gone. It connects us to the earliest moments after the Big Bang, and sets the stage for questions about the ultimate fate of everything. Since Hubble's time, measurements of the expansion have become far more precise. New instruments, space telescopes, and surveys have refined the value of the Hubble constant, the rate at which the universe expands per unit distance. Interestingly, different methods of measuring it today produce slightly different results, a puzzle that has become one of the major tensions in modern cosmology. But whether the exact number is a little higher or lower, the fact of expansion is beyond doubt. The sky is stretching, galaxies are receding, and space itself is dynamic. When you stand outside at night and look up, you are seeing the evidence of this discovery in real time. The photons from distant galaxies have been shifted on their way to you, stretched by the very fabric they travelled through. Every twinkle, every faint glow carries the memory of expansion. The stars feel timeless, but their light is testimony to a universe that refuses to stand still. It's a remarkable thing to consider as you rest tonight. A century ago, the universe was thought to be eternal, unchanging, and limited to the stars we could see. Today, because of a careful set of observations by a patient astronomer with a large telescope, we know we live inside a cosmos that is not only vast but still growing. The discovery of expansion is not just a story about galaxies and light, it is a story about perspective, about how looking carefully at the faintest smudges in the sky can open a window onto the entire history of existence. If the universe is expanding, how exactly should we picture it? How do we explain this motion in a way our minds can grasp when there is no edge or centre? When people first hear that the universe is expanding, the natural instinct is to imagine galaxies flying apart through pre-existing empty space, like shrapnel from an explosion. But that picture is misleading. The expansion is not happening into a void. There is no container outside of the universe into which it grows. Instead, it is space itself that is stretching, carrying galaxies along like driftwood on a rising tide. This idea is difficult to visualize because nothing in our everyday experience resembles it. So physicists and educators often turn to a simple analogy, one that has been used for nearly a century to help explain what an expanding universe really means. It is the image of a balloon and the dots upon its surface. Imagine a balloon resting in your hands. You take a marker and place several small dots on its surface. Each dot represents a galaxy. At first, the balloon is slack, the dots sit close to one another, and the surface area is small. Now begin to inflate the balloon. As it swells, every dot moves away from every other dot. None of the dots is at the centre of expansion, because the expansion is happening everywhere at once. From the point of view of any one dot, all the others appear to be receding, and the farther away a dot is, the faster it seems to move away, because the surface between them is stretching more. That is precisely what astronomers observe in the sky. The power of this analogy lies in its ability to capture a counterintuitive truth. When you look at distant galaxies moving away, it is not because they are propelling themselves through some outer space, but because the fabric between them and us is growing. There is no central point that the galaxies are fleeing from. Every location experiences the expansion equally. If you lived in a galaxy billions of light years away, the view would look much the same. You would see other galaxies rushing away, and you might even come up with your own version of the balloon to explain it. Of course, every analogy has its limits. The balloon expands into the surrounding air, whereas the universe does not expand into anything. The balloon has a centre inside it, while the universe does not have a central point. And the surface of the balloon is two-dimensional, while the real universe has three spatial dimensions. But despite these differences, the balloon model captures the essential feature. Expansion is not motion through space, but the growth of space itself. This can be difficult to internalize because our senses are trained by everyday experiences. When you throw a ball, it travels through the air. When you walk, you move across the ground. You always travel through something from one location to another. But in cosmology, the very coordinates of space are stretching. Galaxies are not flying outward into emptiness. They're carried apart by the stretching fabric of the cosmos. The balloon helps bridge the gap between intuition and reality. There is another helpful element in the balloon picture. Notice that the farther apart two dots are, the more space stretches between them as the balloon inflates. That means the apparent speed of recession increases with distance. This mirrors Hubble's law, which states that recession velocity is proportional to distance. Nearby galaxies appear to drift slowly, while very distant galaxies recede at astonishing speeds. In fact, beyond a certain distance, the expansion of space carries galaxies away faster than the speed of light. This does not violate relativity, because it is space itself expanding, not objects moving through space faster than light. But it does mean that beyond a certain horizon, galaxies disappear forever from our view. Their light will never reach us no matter how long we wait. The balloon analogy also opens the door to thinking about the shape of the universe. The surface of the balloon is finite but unbounded. If you travel in a straight line across it, you never encounter an edge. You could keep going forever, circling back to where you began, and at no point would you hit a boundary. Some cosmologists have suggested that our universe might be like that, finite in volume but without edges. If you could travel far enough in one direction, you might eventually return to your starting point, though on scales so enormous that such a journey is beyond imagination. Current measurements suggest that space is remarkably flat, meaning its geometry may be infinite. But the balloon at least helps us picture how something can be bounded yet edgeless, a concept our everyday intuition struggles with. Now, imagine holding that balloon to your ear, listening as it expands. The faint squeak of rubber stretching is nothing compared to the silent growth of space itself. Yet in a way, the night sky carries the echo of that expansion. The cosmic microwave background is like a snapshot of the balloon when it was still young, a faint glow stretched across the heavens, whispering of the early universe when it was only a few 100,000 years old. The galaxies we see today are like the dots drawn on its surface, pulled apart over billions of years by the inflation of space. For a moment, consider what this means for the night sky you see above you. The constellations are fixed to your eyes, yet over long timescales they change. The stars move relative to one another and galaxies shift. On even longer scales, the very backdrop of galaxies drifts farther away, carried by expansion. The balloon keeps stretching, and the view slowly transforms. Billions of years from now, distant galaxies will be invisible, carried beyond the cosmic horizon. The night sky will grow emptier, its light thinned out by the ever-expanding fabric. For future astronomers, the universe may appear smaller, even as it is truly larger. This is one of the more poignant lessons of the balloon analogy. Expansion not only shapes the past and present, it also shapes what future observers will be able to know. We live in a privileged era where the expansion is clear, where distant galaxies are still visible, and where the cosmic microwave background remains detectable. Future beings may not have access to these clues. Their balloon will be stretched so far that the evidence of its growth will be hidden. For them, the universe might once again appear static as it did for our ancestors. Our moment is a brief window into the truth of expansion. Thinking of the balloon can also lead you into the question of what lies beyond. If the balloon's surface represents our universe, what about the inside and the outside? In the analogy, those regions exist in our three-dimensional world, but they are not part of the two-dimensional surface that represents the cosmos. Similarly, When cosmologists say the universe is all there is, the outside has no meaning within the model. Asking what lies beyond is like asking what is north of the North Pole. The balloon is sufficient unto itself. Yet our minds resist this closure. We crave an exterior, a beyond. The analogy shows us why that craving may not fit the structure of reality. Still, it remains one of the most effective tools for teaching the expansion. Children can see it with their own eyes when they blow up a balloon with dots drawn on it. Students can measure distances and compare them before and after inflation. And adults can carry the image in their minds when they look up at the sky, reminding themselves that galaxies are dots on a balloon, too vast for us to ever see in its entirety. It is a humble image, made of rubber and air, yet it holds within it the essence of the universe's motion. In the early years of the 20th century, astronomy was a field undergoing transformation. Telescopes were growing larger, cameras more sensitive, and the night sky was being recorded in greater detail than ever before. At the heart of this quiet revolution stood a man whose name would eventually become synonymous with the universe itself, Edwin Hubble. He was not the first to look at the heavens, nor the only one to wonder what those faint smudges of light might be, but he was the one who connected the dots, literally and figuratively, between those faint patches and the vast structure of the cosmos. His work shifted humanity's place in the universe, and though he was a reserved man, the impact of his discoveries was thunderous. Hubble's story begins in Missouri, where he was born in 1889. By the time he reached adulthood, he had studied mathematics and astronomy, though his path was not straightforward. He also trained in law, spent time as a school teacher, and even served briefly in the military. But eventually, his pull toward the stars proved irresistible. After completing his doctorate in astronomy at the University of Chicago, he secured a position at the Mount Wilson Observatory in California, which housed the 100-inch Hooker telescope. At the time, it was the largest telescope in the world, and it opened a window onto the universe that no human eye had seen before. Mount Wilson was perched high in the San Gabriel Mountains, above much of the haze and light of Los Angeles. The observatory's location offered clear, dark skies, perfect conditions for exploring the faintest reaches of the cosmos. From this mountaintop, Hubble began to study the mysterious nebulae that had puzzled astronomers for centuries. These objects appeared as faint, fuzzy patches of light. Some believed they were clouds of gas within our own galaxy. Others suspected they might be entire galaxies themselves far beyond the Milky Way. The question had come to be known as the Great Debate, and the answer would redefine the scale of the universe. Hubble's breakthrough came through his careful study of Cepheid variable stars within these nebulae. These stars pulsate in brightness with a regular rhythm, and the period of their cycle is directly linked to their true luminosity. By measuring their brightness and comparing it with their intrinsic power, astronomers can determine their distance. When Hubble identified Cepheid variables inside the Andromeda Nebula, he realized they were far too distant to belong to the Milky Way. The Andromeda Nebula was not a cloud within our galaxy at all. It was another galaxy entirely, containing billions of stars of its own. This discovery shattered the old conception of the universe. The Milky Way was no longer the whole cosmos, but just one galaxy among many. In an instant, the known universe grew unimaginably larger. What had once been thought of as the totality of existence was revealed to be a single island in a vast cosmic ocean. Humanity had been displaced once before, when Copernicus showed that the Earth was not the centre of the solar system. Now it was displaced again, our galaxy reduced to just one among countless others. But Hubble's work did not stop with the identification of galaxies. As he measured the light from more and more of these distant systems, he noticed a consistent shift toward the red end of the spectrum. This redshift suggested that the galaxies were moving away from us, and when Hubble plotted their velocities against their distances, he found a simple, linear relationship. The farther away a galaxy was, the faster it receded. This pattern became known as Hubble's law, and it revealed that the universe itself was expanding. The significance of this was profound. For centuries, philosophers and scientists had assumed that the universe was static and eternal. Even Einstein, whose equations of general relativity predicted that space could expand, had altered his own mathematics to force a steady state, adding a cosmological constant to cancel out the motion. When Hubble's observations showed the expansion was real, Einstein reportedly admitted that removing it had been a mistake. The universe was not fixed. It was dynamic, changing, evolving. Hubble himself was not one to boast about the philosophical implications of his discoveries. He presented his results with a quiet formality, emphasizing the data rather than sweeping interpretations. But others quickly recognized the meaning. Georges Lemaitre, a Belgian priest and physicist, had already proposed that the universe might have begun from a primeval atom that exploded outward. Hubble's law gave his idea empirical support. The universe had a beginning, and it was still in motion. What had once seemed eternal now had a history. Working at Mount Wilson, Hubble was surrounded by other astronomers who were piecing together parts of the same puzzle. Milton Humason, a former mule driver turned telescope operator, became Hubble's close collaborator, helping him gather the spectroscopic data that revealed the redshifts of galaxies. Their teamwork produced the measurements that underpinned Hubble's law. While Hubble often received the credit, Humason's skill and perseverance were essential to the work. The quiet revolution of expansion was not the product of one man alone, but of many hands and minds. The impact of Hubble's discoveries rippled far beyond astronomy. Philosophers, theologians, and ordinary people grappled with the idea of a universe that was not infinite and unchanging, but finite in age and dynamic in structure. For some, it was exhilarating. For others, unsettling. But for science, it was a turning point. Cosmology became an empirical discipline, grounded in observation rather than speculation. The universe could be measured, charted, and understood, not just imagined. Hubble's own demeanour was reserved, almost austere. He carried himself with a sense of authority, sometimes even aloofness, and cultivated an image of refinement. Yet his quiet manner belied the radical nature of his contributions. He was in many ways a man of contradictions, both meticulous scientist and larger-than-life figure, both humble in his presentation and ambitious in his reach. The revolution he began was not one of sudden upheaval, but of steady accumulation, observation by observation, until the picture of the cosmos shifted irreversibly. As the years passed, Hubble's name became attached not only to the law of expansion, but also to one of humanity's greatest scientific instruments, the Hubble Space Telescope. Launched in 1990, decades after his death, the telescope has carried his legacy forward, peering deeper into the cosmos than he ever could have imagined. Its images of galaxies, nebulae, and the farthest reaches of space are the descendants of the faint smudges he studied at Mount Wilson. Each photograph is a tribute to the quiet revolution he set in motion. The story of Hubble reminds us that great changes often begin in small, quiet places. A mountaintop observatory, a patient observer hunched over glass photographic plates, a few faint stars identified among smudges of light. From those humble beginnings came the realization that the universe is far larger and more dynamic than anyone had dared to imagine. And once you see that, you cannot unsee it. The cosmos expands not only in fact but in the human mind, reshaping our sense of where we belong. As you drift deeper into rest, imagine yourself at Mount Wilson in the 1920s. The dome of the great telescope creaks as it turns. The night air is cool and still. Hubble peers through the eyepiece, noting the faint glow of galaxies whose light has travelled millions of years. Somewhere, a photographic plate records the spectrum of a star, its lines shifted redward by the universe's stretch. In that quiet, the revolution begins. The galaxies move. The universe expands, and humanity takes another step outward into the vast unknown. How do we measure such motion? How do we know the rate of expansion? and how has our ability to measure it improved since Hubble's time? When Edwin Hubble first traced the relationship between distance and velocity, his work relied on a handful of galaxies and some of the most delicate measurements available at the time. It was enough to reveal the expansion, but not nearly enough to define it with precision. That task would fall to later generations of astronomers who would spend decades refining their methods, building more powerful instruments, and inventing clever new ways to measure the stretch of space. To this day, the effort continues. The expansion is not just a fact, it is a number, a rate, and nailing down that number has become one of the central pursuits of modern cosmology. The key idea is simple enough. If galaxies are moving away from us, and the speed of their recession increases with distance, then the slope of that relationship gives us the expansion rate of the universe. This slope is called the Hubble constant, usually expressed in kilometers per second per megaparsec. A megaparsec is a little more than 3 million light years, so the units mean this. For every megaparsec of distance, a galaxy recedes that many kilometers per second faster. It is the cosmic speedometer, the ruler by which the universe measures its own growth. But measuring it precisely is anything but simple. To know the rate of expansion, you must know both distances and velocities. Velocities come from redshifts, which are relatively straightforward to measure by examining the spectra of galaxies. Distances, however, are far trickier. The universe does not come with mile markers. To gauge how far away something is, astronomers must build what is often called the cosmic distance ladder. Each rung of this ladder relies on a particular method, and together they climb from the nearest stars to the farthest galaxies. At the bottom of the ladder are parallax measurements. Parallax is the apparent shift of a nearby star against the background, when observed from two different positions of Earth in its orbit. This method provides direct geometric distances to stars within a few thousand light years. Space missions like Hipparcos and Gaia have extended parallax to unprecedented precision, mapping millions of stars with exquisite accuracy. From there, astronomers move up to standard candles, objects whose intrinsic brightness is known. By comparing their true luminosity with how bright they appear, the distance can be inferred. Cepheid variable stars are one of the most important standard candles. Their predictable pulsation makes them reliable yardsticks, and Hubble himself used them to measure the distance to Andromeda. Later, astronomers added type Ia supernovae to their toolkit. These exploding stars shine with nearly uniform brightness, making them excellent markers for even greater distances. By combining parallax, cepheids, and supernovae, astronomers can trace distances from our galactic neighbourhood to galaxies hundreds of millions of light years away. With redshifts providing velocities, the expansion rate can be plotted. But even with these methods, uncertainties creep in. How well do we understand the intrinsic brightness of cepheids? Are there subtle variations in supernovae? Each refinement brings the number closer into focus, but it also opens the door to debate. In recent decades, space telescopes have pushed the effort further. The Hubble Space Telescope, named in honour of Edwin Hubble, has played a central role in measuring Cepheid variables in distant galaxies, free from the blurring effects of Earth's atmosphere. Observations of supernovae with Hubble and other instruments revealed not only the expansion but also its acceleration, driven by the mysterious force we call dark energy. These discoveries have added both clarity and complication to the story of measurement. One of the most intriguing developments in recent years has been the discrepancy between different methods of measuring the Hubble constant. When astronomers use the distance ladder, parallax, cepheids, and supernova, they arrive at a value around 73 km per second per megaparsec. But when they use observations of the cosmic microwave background, the relic radiation from the early universe, combined with the theory of cosmology, they find a lower value, around 67. This tension, known as the Hubble Tension, has persisted despite increasingly precise measurements on both sides. It may point to new physics, or it may reveal unknown systematics in the data. Either way, it has become one of the hottest topics in cosmology. To understand why the cosmic microwave background gives a different answer, you have to imagine the universe not as it is today, but as it was nearly 14 billion years ago. The microwave background is the afterglow of the Big Bang, stretched to millimetre wavelengths by expansion. Tiny fluctuations in its temperature encode information about the density and composition of the universe at that early time. By modelling how those conditions evolved, cosmologists can predict the expansion rate today. The Planck satellite, which measured the microwave background with stunning precision, provided the lower value of the Hubble constant. The disagreement with local measurements is not easily dismissed, and so the stretch of space remains not just a measurement but a mystery. Other approaches are being explored to help resolve the tension. Gravitational lensing, where the light of distant galaxies is bent by massive foreground objects, can be used to measure distances and expansion rates. So can gravitational waves, ripples in space-time caused by merging black holes or neutron stars. When such an event is observed both in light and in gravitational waves, it provides a new kind of standard candle, sometimes called a standard siren. As detectors improve, these events may add fresh rungs to the distance ladder and provide independent checks on the Hubble constant. For now, the measurement of expansion is one of those curious places where science thrives, a region of uncertainty. The numbers are close enough to agree on the broad picture. Yes, the universe is expanding, and yes, its age is about 13.8 billion years, but far enough apart to keep researchers awake at night. Somewhere in that discrepancy may lie the hint of new physics, perhaps related to dark energy, dark matter, or even modifications of gravity itself. Measuring the stretch of space is not just an exercise in precision, it is a window into the fundamental workings of reality. It's worth pausing to reflect on how extraordinary this all is. From a mountaintop in California, Edwin Hubble traced faint smudges of light on glass plates and found a law that reshaped the universe. Today, satellites in space and detectors on Earth continue that work, refining the slope of the line he first drew. The effort spans generations, instruments, and continents. And yet, at its heart, it is about the same simple question. How fast is the universe growing? As you rest now, think of the expansion as a rhythm. The galaxies drift apart, the light stretches, the fabric of space hums with its steady growth. Astronomers measure that rhythm in kilometers and megaparsecs, but you can feel it in another way. It is the passage of time, the change of seasons, the way even the most solid-seeming things are never truly fixed. To measure the stretch of space is to measure change itself, written on the largest canvas imaginable. If space is expanding, what force is behind it? Why is the expansion not slowing under the pull of gravity, but accelerating instead? When people first began to measure the expansion of the universe, the natural assumption was that it must be slowing down. After all, gravity pulls things together. If galaxies are receding because of the initial momentum of the Big Bang, then their motion should gradually be decelerating under the mutual pull of their mass. Astronomers expected that by studying the rate of slowdown, they could learn whether the universe would one day halt and collapse back on itself, or whether it would coast forever, slowing but never stopping. What they did not expect was that the expansion would be doing the opposite. In the late 1990s, two independent teams of astronomers set out to measure the rate of deceleration by observing distant Type Ia supernovae. These stellar explosions are so bright that they can be seen across billions of light years, and because they have nearly uniform intrinsic brightness, they serve as excellent standard candles. By comparing their apparent brightness with their redshift, astronomers can calculate both their distance and the rate at which the universe was expanding when their light was emitted. The results were startling. Instead of finding that the expansion was slowing, the teams discovered that it was accelerating. The universe was not only growing larger, but it was doing so faster and faster. Galaxies were not merely coasting apart, they were being pushed apart by some unknown force. This was one of those rare moments in science when the data were so surprising that they overturned the expectations of nearly everyone involved. The discovery earned the Nobel Prize in Physics in 2011, but more importantly, it introduced one of the greatest mysteries in modern cosmology, the phenomenon we now call dark energy. Dark energy is a placeholder name, a label for something we do not yet understand. It appears to be a property of space itself, a form of energy that exerts a repulsive effect, counteracting gravity on the larger scales. Unlike dark matter, which interacts gravitationally and can clump to form structures, dark energy does not gather into halos or galaxies. It is smooth, uniform and pervasive, woven into the very fabric of the cosmos. Current estimates suggest that nearly 70% of the energy content of the universe is in this form. Everything we see, stars, planets, gas, dust, makes up less than 5%. Dark matter accounts for about a quarter, and dark energy dominates the rest. The universe, in other words, is mostly made of something we do not yet comprehend. One way to picture dark energy is to think of the cosmological constant Einstein once introduced into his equations. He added it to force the universe into a static state, but it can also be interpreted as a vacuum energy, a kind of constant push inherent in empty space. If every cubic meter of space contains a small amount of energy, then as the universe expands and more space appears, the total effect increases, driving faster expansion. This interpretation matches the observations reasonably well, but it raises profound questions. Why should empty space have energy? Why this amount and not another? Another possibility is that dark energy is not constant but dynamic, perhaps related to a new field that changes over time. Some theorists call this quintessence, a hypothetical energy field that evolves as the universe expands. If dark energy is quintessence, its influence may grow or diminish in the future, altering the ultimate fate of the cosmos. But so far, observations have not shown any deviation from the simplest model of a constant vacuum energy. For now, the cosmological constant remains the leading explanation, even if it feels deeply unsatisfying. The mystery of dark energy is sharpened by a striking problem known as the cosmological constant problem. When physicists calculate the energy of the vacuum using quantum field theory, the result is vastly larger, by a factor of up to 10 to the 120, than what is observed in cosmology. This is sometimes called the worst theoretical prediction in physics. Why the observed value is so small, yet not zero, is an open puzzle. It suggests that something fundamental is missing from our understanding, perhaps a connection between quantum mechanics and gravity that has not yet been discovered. On a practical level, dark energy changes how we imagine the future of the universe. If the expansion is accelerating, then galaxies will continue to recede faster and faster. Already, galaxies beyond a certain distance are moving away faster than light, not because they are travelling through space at superluminal speeds, but because space itself is stretching between us. Their light will never reach us, no matter how long we wait. As acceleration continues, more galaxies will cross this horizon, vanishing from view. Over time, the night sky will grow emptier. Future observers in our galaxy may see only a handful of nearby systems, unaware of the vast cosmos we know today. In some models, dark energy could even lead to a dramatic end known as the Big Rip. If the acceleration grows without limit, it could eventually overcome not just the gravity binding galaxies, but the forces holding stars, planets, and even atoms together. In this scenario, the universe would tear itself apart, ending in a final disintegration. Whether this fate awaits us depends on the nature of dark energy. If it is a true cosmological constant, the expansion will accelerate forever, but never reach the catastrophic rip. If it is more exotic, the future could be stranger still. The discovery of dark energy has had another curious effect. It reshaped how we view cosmic balance. For decades, cosmologists had debated the density of matter in the universe, asking whether it was enough to halt expansion. The idea of a critical density determined whether the cosmos was open, closed, or flat. With dark energy in the picture, the debate shifted. The geometry of the universe appears flat, but not because matter alone provides the critical density. Instead, dark energy makes up the difference, balancing the books in a way no one anticipated. It is humbling to realize how recently we learned of this. Just a generation ago, the term dark energy did not exist. Cosmology textbooks described a universe of matter and radiation, perhaps open or closed, destined to expand forever or collapse in a big crunch. The discovery of acceleration forced a rewrite of that story. It revealed that the most important component of the cosmos is one we cannot see, touch, or fully explain. And it left us with the strange sense that we live in a universe ruled by something invisible, a quiet force shaping the fate of everything. As you let your mind drift with this thought, imagine the galaxies sliding away across the cosmic fabric. Not with the inertia of an explosion, but with the steady push of dark energy, a pressureless, invisible presence that fills the void. It does not shine, it does not cluster, it does not announce itself, yet it holds sway over 70% of the cosmos. The stars overhead are only the tip of the iceberg. Beneath them lies a vast sea of unknown influence. Across the night sky, galaxies appear as delicate smudges of light, faint glows that blend almost imperceptibly with the darkness. Through a backyard telescope, they may look like pale spirals or faint ovals, but to sensitive instruments they reveal themselves as sprawling collections of hundreds of billions of stars, each star orbited by planets, each galaxy drifting across cosmic distances. To the naked eye, they seem timeless, frozen in place, but in truth, they are on the move. They are participants in a vast, ongoing migration, a race not toward any particular finish line but away from one another, carried apart by the expansion of the universe. The phrase, "galaxies on the run," captures this strange reality, though it is not their engines propelling them, but the growth of space itself. If you could watch the universe sped up like a time-lapse film, the motion would become obvious. Galaxies would recede in all directions, filaments of cosmic structure stretching like taffy, voids between clusters swelling ever larger. The galaxies themselves would not blur apart, for gravity binds them tightly. Stars remain in orbit around galactic centers, and galaxies remain bound within clusters. But the space between clusters, between great walls of galaxies, swells relentlessly. In this accelerated view, you would see entire regions of the cosmos slip from visibility, their light stretched so thin that it fades beyond detectability. To stand at the centre of such a film is to witness a cosmos in constant retreat, where every point seems to move away from every other. From our vantage point in the Milky Way, this grand drift is both subtle and profound. The Andromeda Galaxy, our nearest large neighbour, is in fact approaching us, drawn by mutual gravity. In a few billion years, the two will collide and merge into a new galaxy, sometimes nicknamed Milkomeda. On local scales, gravity dominates, knitting galaxies together into groups and clusters. But step back farther, and the pattern shifts. Beyond our local group, galaxies as a whole are receding, and the farther away they are, the faster they run. The Virgo cluster, for example, lies about 50 million light-years away, and its galaxies recede at hundreds of kilometers per second. Beyond that, superclusters stream away at thousands of kilometers per second. Across billions of light-years, the speeds approach a fraction of the speed of light itself. This motion is not noise or random wandering. It follows a clear law, the one Hubble traced in the 1920s. Distance and velocity rise together in a simple linear relation. But to call it simple is deceptive, because the implications are staggering. The universe itself is stretching, carrying galaxies apart not like ships sailing away on an ocean, but like dots painted on a balloon that grows larger. No one is at the centre of this flight. Every galaxy sees the others receding, each from its own perspective. To live in such a universe is to inhabit a cosmos without a preferred position, where all observers are equal witnesses to the expansion. One of the most poignant aspects of this galactic race is that it will ultimately thin the cosmos before our eyes. Already there are galaxies whose light will never reach us, carried away faster than photons can bridge the gulf. They lie beyond our cosmic horizon, out of reach not because they are hidden behind walls or obstacles, but because the fabric of space grows too quickly. Their stories are cut off from ours, their light lost forever to our perspective. The observable universe is like a shrinking bubble in an expanding ocean. What we can see grows smaller in proportion, even as the whole grows larger. To contemplate galaxies on the run is to consider time as much as space. The light we see from distant systems left them millions or billions of years ago. We do not see them as they are, but as they were. Some may already have merged, changed, or vanished. Their current state is unknowable to us, hidden behind the delay of light and the speed of expansion. In a sense, the sky above is not just a map of space, but a museum of time, filled with ancient snapshots carried across the void. Each galaxy's apparent retreat is also its history, written in photons stretched red by the growing cosmos. Even within the Milky Way, the awareness of motion is humbling. Our own galaxy drifts at hundreds of kilometers per second relative to the cosmic microwave background, the faint afterglow of the Big Bang. Against that backdrop we can measure our peculiar motion, our local drift within the larger flow. The Milky Way, Andromeda, and their companions fall together toward the centre of the local group, which itself streams toward the Virgo cluster. And beyond that, the entire region is drawn toward a gravitational anomaly astronomers call the Great Attractor, a dense region of mass hundreds of millions of light-years away. On the grandest scales, flows of galaxies weave like rivers, converging on massive structures even as the fabric itself pulls everything apart. These layers of motion might seem contradictory, galaxies racing away, yet also falling toward attractors, clusters receding, yet locally bound. But together they form a coherent picture, one where gravity rules nearby and expansion rules afar. It is like watching ripples on a river. The surface flows downstream, carrying everything along, but within it, eddies and whirlpools swirl on smaller scales. Galaxies on the run are like those ripples and eddies, drawn together locally but carried outward in the larger stream. The notion of galaxies on the run also changes how we think about the fate of the universe. If dark energy continues to accelerate expansion, then the recession will only intensify. In the far future, galaxies not gravitationally bound to us will disappear from view. The night sky will fade, stripped of its distant beacons. Future astronomers may live in a cosmic solitude, surrounded only by their own merged galaxy and a few nearby dwarves, unaware of the grand expanse we now glimpse. The universe will still teem with galaxies, still run with expansion, but those galaxies will no longer share their light with us. Their race will continue unseen. It is remarkable to think that all of this, the running of galaxies, the stretching of light, the vanishing of horizons, was hidden from human awareness until just a century ago. For millennia, the stars appeared fixed, the heavens unchanging. Then a few careful observations revealed the truth. The universe is restless, dynamic, and forever in motion. Galaxies are not quiet islands, but travellers, caught in a cosmic current too vast to resist. Their flight is silent, but it leaves its imprint in every spectrum we measure, every redshift we record, every dim supernova we chart. As you let your thoughts drift, picture those galaxies as lights receding into a deepening twilight. Each carries within it billions of suns, countless planets, perhaps even other beings wondering about their place in the cosmos. Yet all are swept up in the same expansion, carried apart by the same invisible force. Their paths diverge endlessly, and still the race goes on. The running of galaxies is not a temporary phase, but the ongoing story of existence itself. If galaxies are fleeing into the dark, what becomes of the night sky as ages pass? How will the canvas of stars evolve as expansion and acceleration carry the galaxies farther and farther away? If you step outside on a clear evening and look upward, the night sky feels timeless. The stars are steady companions, their constellations familiar, their patterns unchanged across generations. The Milky Way stretches as a pale band, hinting at the multitude of suns beyond our own. For most of human history, this view seemed eternal. People navigated by the stars, told stories about them, and built monuments aligned with their positions, trusting that the sky was fixed. Yet when we think carefully about what we now know, the expansion of the universe, the drift of galaxies, the acceleration driven by dark energy, it becomes clear that the night sky is not eternal at all. It is changing. Its fate is written in the same expansion that drives galaxies apart, and the canvas we see today is just one fleeting frame in a much longer film. The first and most obvious change is slow but already underway. The constellations themselves are not truly permanent. Stars move through the galaxy at different speeds and along different paths. Over thousands or millions of years, the shapes we know, Orion's Belt, the Big Dipper, the Southern Cross, will warp and twist as stars drift into new configurations. To our eyes, the constellations look frozen, but in reality they are like a snapshot of dancers caught mid-step. The choreography continues slowly, unnoticed on human timescales but inevitable in the long view. Beyond the slow drift of stars, there is the motion of entire galaxies. The Milky Way and the Andromeda Galaxy are on a collision course, drawn together by gravity despite the overall expansion. In about 4 billion years they will meet and merge. The process will take another billion years or so, a drawn-out encounter where stars mostly pass by one another, but the galaxy's shapes distort and stretch into tidal tails. Eventually, the two will settle into a single giant elliptical galaxy. For observers in that distant future, the night sky will be dramatically altered. Instead of the familiar band of the Milky Way, they will see a vast glowing core stretching across the heavens, filled with billions of merged stars. But even as our local group of galaxies evolves in this way, the larger universe will continue to drift away. Already, galaxies beyond a certain distance are receding faster than light, carried beyond our cosmic horizon by the expansion of space. Their light will never reach us, no matter how long we wait. As dark energy continues to accelerate the expansion, more and more galaxies will cross that horizon. One by one, they will vanish from view, leaving only the galaxies bound to us by gravity. In the far future, perhaps tens or hundreds of billions of years from now, the night sky will be far emptier than it is today. The countless galaxies we can now observe with telescopes will be gone, their light stretched beyond detection, their presence erased from the observable cosmos. For astronomers in that era, the universe may appear small and lonely. They may see only their own merged galaxy, surrounded by a few dwarf companions. The cosmic microwave background, the faint afterglow of the Big Bang, will also fade, its wavelength stretched so far by expansion that it becomes undetectable. All the evidence we now rely on to understand cosmic history, the redshifts, the background radiation, the distant galaxies, will no longer be accessible. It is a sobering thought. Our moment in cosmic history is uniquely privileged. We live at a time when the universe is old enough for galaxies to have formed and spread out, but not so old that they have all disappeared beyond the horizon. We have access to clues that future astronomers may never have. To them, the night sky will tell a very different story. Without the evidence of expansion, they might conclude that their galaxy is the whole universe, just as people once did here on Earth. the grand discoveries of cosmology could be lost, hidden by the very acceleration that revealed them to us. On shorter timescales, the fate of the night sky includes other transformations as well. Stars themselves are not eternal. They live finite lives, burning their nuclear fuel before evolving into white dwarfs, neutron stars, or black holes. The bright stars we see in the constellations are often massive, with lifespans of only tens of millions of years. In cosmic terms, that is a blink of an eye. Already many stars visible in ancient skies have long since died, their light continuing to arrive here long after their demise. In the future, the familiar bright beacons of our sky will vanish, replaced by new stars born in the Milky Way's spiral arms. The sky is dynamic, not fixed, and its appearance is always shifting, even if the changes are too slow for us to notice within a lifetime. If we extend our gaze into the distant future, beyond the merger of the Milky Way and Andromeda, beyond the vanishing of galaxies over the horizon, we reach a universe dominated by red dwarfs, the longest-lived stars. These small dim stars can burn for trillions of years, far longer than the universe has existed so far. For observers living in those eras, the night sky will be populated mainly by faint red points, not the brilliant white and blue stars we see today. The sky will be darker, calmer, and slower in its rhythms. The sparkling constellations we know will be gone, replaced by a quiet glow of long-lived stars. Eventually, even star formation will cease. The raw gas needed to form new suns will be used up or locked away in remnants. The galaxies will grow dim, populated only by cooling remnants and fading dwarfs. The night sky will lose its brilliance, not in a sudden collapse, but in a gradual fading. Trillions of years from now, starlight will be rare, and the heavens will look very different indeed. This long view of the sky's fate can feel melancholy, but it also adds a layer of wonder to the view we have today. To step outside tonight and look up is to see the sky at a moment of fullness, a time when bright stars, active galaxies, and the glow of the Milky Way all coexist. It is a fleeting window in cosmic history, and we happen to be alive to witness it. The constellations we trace, the galaxies we map, the faint radiation we measure, these are gifts of timing as much as of science. As you drift deeper into rest, picture the night sky not as fixed but as alive. Imagine the stars as travellers, each with its own path, its own lifespan, its own story. Imagine the galaxies receding, their light stretching into invisibility. Imagine the slow fading of starlight, the dimming of the cosmos, the way the sky itself evolves as the universe ages. The fate of the night sky is to change, always, forever. And in knowing that the stars above tonight become all the more precious, each one a spark in a sky that will never be the same again. From here, it is natural to wonder about the limits of what we can see. If galaxies vanish beyond horizons, if the sky itself fades, then what defines the boundary of our vision? How far can we look? And what lies beyond that cosmic curtain? When we think of horizons in everyday life, we imagine the line where the sea meets the sky, or the edge of a valley where mountains rise. A horizon marks the limit of what can be seen, not because the world ends there, but because our vantage point does. If you travel farther, the horizon shifts with you. There is always more land or ocean beyond, hidden only by the curve of the Earth. In cosmology, horizons have a similar meaning. They are not walls, not boundaries of the universe, but limits to our vision, defined by the physics of light and the expansion of space. To talk about cosmic horizons is to talk about how far our eyes and instruments can reach and what lies forever beyond our sight. The first kind of horizon is the simplest, the particle horizon, which marks the maximum distance from which light could have travelled to us since the beginning of the universe. Light moves fast, nearly 300,000 kilometers per second, but the universe has a finite age. 13.8 billion years is an immense span, but it is not infinite, and so there is a maximum distance photons can have travelled since the Big Bang. You might think this would limit our view to about 13.8 billion light-years, but the expansion of space complicates things. While the light was travelling, the fabric of space was stretching, carrying its source farther away. As a result, the most distant regions we can see today are not 13.8 billion light-years distant, but closer to 46 billion. The observable universe is larger than the naive calculation suggests, not because light outran its own speed, but because the very stage it crossed was stretching all the while. Another kind of horizon, equally important, is the event horizon. This one marks the boundary beyond which events can never affect us, no matter how long we wait. It is shaped by the accelerated expansion driven by dark energy. Galaxies beyond a certain distance are receding faster than light can bridge. Their signals will never reach us, even if we wait until the end of time. This event horizon is like a cosmic point of no return, a region where galaxies slip away not just from our current vision, but from any possibility of future contact. Their light is lost forever to us, sealed beyond a barrier that is not physical but woven into the fabric of space-time itself. There is also the horizon of the past, the surface of last scattering, which we see as the cosmic microwave background. This is the oldest light we can observe, released when the universe was only about 380,000 years old. Before that time, the cosmos was a hot, dense plasma, where photons could not travel freely. The universe was opaque, like the interior of a star. Only when it cooled enough for atoms to form did light decouple from matter and begin streaming through space. That light still fills the cosmos today, stretched into microwaves by expansion. It is a horizon in time, a wall we cannot see beyond because no photons from earlier epochs could travel freely. These horizons frame our view. They define the observable universe, everything we can see, measure, and study. But they do not define the universe itself. Beyond the horizons, the cosmos continues, perhaps infinitely. We cannot observe it directly, but theories suggest that the universe extends far beyond what we can detect. Our view is a bubble, bounded by horizons, but the true expanse may be much larger, perhaps unimaginably so. It is worth reflecting on how peculiar this is. We live in a universe with edges of visibility, but not edges of existence. The observable cosmos is like the patch of ocean visible from a ship's deck. You see the water curve away, you see the line of the horizon, but you know the ocean continues. Our observable patch is immense, containing hundreds of billions of galaxies, each with billions of stars. Yet it may be just one portion of a vastly larger whole. Cosmic horizons are not static. As time passes, the particle horizon grows. New light from distant regions arrives, adding more to our observable universe. We can see farther than our ancestors could, and future observers will see farther still. At the same time, the event horizon shrinks in a sense. As expansion accelerates, more galaxies cross that boundary of no return, vanishing from view. Horizons open and close, shifting what is visible and what is lost. The universe is dynamic not only in its expansion, but in the very limits of sight it grants us. The horizons also raise profound philosophical questions. If we cannot see beyond them, can we ever know what lies outside our observable patch? Are the laws of physics the same beyond our reach? Is the distribution of galaxies similar, or might the universe look radically different elsewhere? In principle, we cannot know. Observations are bounded. Yet cosmologists often assume what is called the cosmological principle, that on large scales the universe is homogeneous and isotropic, the same everywhere and in every direction. It is a practical necessity, for without it the problem becomes unsolvable. But it is also an assumption, one we cannot test beyond our horizons. In some theories, horizons themselves have deeper meaning. In black hole physics, horizons mark the boundaries of no return, regions beyond which information cannot escape. The universe's event horizon is an echo of that concept, a cosmic scale parallel. It suggests that the universe itself has a kind of information boundary, a limit to what can ever be known. Some theorists even argue that the horizon may encode information, that the universe could be described holographically on its boundary. These are bold ideas, still speculative, but they highlight how horizons are not merely observational inconveniences. They may be windows into the deepest workings of reality. For the person standing under the night sky, though, horizons are simply limits of sight. You look up, and beyond a certain distance, you cannot see. It is not that nothing exists there, but that existence is hidden by the speed of light and the growth of space. To know this is both humbling and strangely comforting. It reminds us that knowledge has boundaries, that some mysteries will always lie beyond reach. The cosmos is larger than what we can observe, and that largeness is part of its beauty. As you let this thought settle, imagine the universe as a great sphere of visibility around you. Within it, galaxies shine, clustered into filaments, connected by webs of dark matter, their light reaching us across billions of years. At the edge lies a faint glow, the microwave background, a remnant of the young universe. Beyond that, darkness. Not emptiness, but silence. The silence of regions we cannot know. The horizons are not barriers but reminders. They tell us that we live inside a window, and that outside the glass reality continues unseen. If our view is bounded, if horizons limit what we can see, then what can we say about what lies beyond? What does the universe contain outside our bubble of visibility? When we speak of the observable universe, we're really speaking of a limit, a bubble of visibility carved out by the finite speed of light and the expansion of space. Inside that bubble, we can trace galaxies, clusters, cosmic filaments, and the faint microwave glow left over from the Big Bang. It is a vast domain, unimaginably large compared to anything in our everyday lives, and yet it is still a fragment. Beyond the edge of observation lies more universe. How much more, we cannot say. The question of what lies beyond what we can see has haunted astronomers, philosophers, and dreamers alike for generations. It sits at the border between physics and imagination, where evidence thins but curiosity persists. The simplest possibility is that the universe beyond our horizon looks very much like the universe within it. This assumption is rooted in the cosmological principle, the idea that on large scales the cosmos is homogeneous and isotropic. It doesn't matter where you are or which direction you look, the laws of physics are the same, the distribution of galaxies statistically similar. If that principle holds beyond our horizon, then the unseen universe is a continuation of the seen. There are more galaxies, more filaments, more voids stretching outward without end. Our observable bubble is like a patch of quilt, and the quilt extends far beyond what we can ever touch. But what if the principle does not hold? What if the regions beyond our horizon are different? Some theories suggest that the universe might not be uniform on the very largest scales. Perhaps there are vast regions with different densities, different cosmic histories, even different laws of physics. If inflation, the rapid expansion, thought to have occurred in the earliest moments of the universe, is true, then the cosmos may be much larger than our observable portion, perhaps infinite. Inflation could also create pocket universes, regions where space stopped inflating at different times, each with its own conditions. In that case, what lies beyond what we can see may not be just more of the same, but something radically different. Consider, for example, the idea of cosmic variation in physical constants. Within our observable universe, the strength of gravity, the charge of the electron, and the speed of light appear fixed. But could those values differ elsewhere? In some models of inflation, different regions of space might settle into different configurations, producing different physics. In one bubble, stars and galaxies form much as they do here. In another, conditions might prevent stable atoms or accelerate the collapse of matter before life can arise. If such regions exist, they lie beyond any possible observation, yet their possibility reshapes how we think about our own cosmic patch. Another layer of speculation comes from the concept of the multiverse. In some theories, inflation is eternal, space continues inflating in most regions, while small patches stop and form bubble universes like ours. If so, then what lies beyond what we can see may not even be part of our universe in the usual sense. It may be other universes disconnected from ours except in their shared origin. These other universes might obey different rules, host different forms of matter, or remain sterile and lifeless. The multiverse idea is controversial because it stretches the boundary of science toward what may never be testable, yet it arises naturally in some versions of our best theories, and so it cannot be ignored entirely. Even if we set aside the multiverse, the sheer scale of the unseen universe is staggering. Remember that the observable cosmos is defined by light travel time. As time goes on, new light arrives from farther regions, expanding our horizon. Billions of years from now, the observable universe will be larger, though not infinitely so because of the accelerating expansion. But even then, the universe as a whole may stretch far beyond. We are like people in a dense fog, able to see a few meters in every direction. Beyond that, the fog continues, but we cannot see how far. Our patch feels large, but it may be a tiny fragment of an incomprehensibly vast whole. It is worth remembering that our ancestors once thought the world ended at the edge of their maps. Beyond lay sea monsters, uncharted waters, speculation. With time, the maps grew, the monsters retreated, and the Earth was revealed as a sphere with no edges. Today, we find ourselves in a similar position on a cosmic scale. Our maps extend 46 billion light-years in all directions, bounded by the microwave background. Beyond that we cannot see. Does the map end there? Or does the universe continue, indifferent to our limits of vision? Most cosmologists suspect the latter. The horizon is not the end, but the beginning of what we cannot know. There is also a more subtle possibility, that beyond what we can see lies not a spatial continuation, but a temporal one. The observable universe is a view of the past. When we look outward, we look backward in time, seeing galaxies as they were billions of years ago, seeing the microwave background as it was nearly 14 billion years ago. Beyond that lies the epoch before light could travel freely, the first 380,000 years after the Big Bang. And beyond even that lies the realm of inflation, the Planck epoch, the birth of space-time itself. These regions are hidden not by distance but by physics. We cannot see them because light could not carry their story, yet they exist as part of the universe's past, just as real as the galaxies we observe. So what lies beyond what we can see? Perhaps more galaxies, perhaps other universes, perhaps eras of cosmic history forever hidden from photons, perhaps all of these at once. The truth is that we do not know and may never know, but this ignorance is not a failure. It is an invitation. The edge of observation is the edge of imagination, the place where questions bloom. Every telescope, every detector, every survey pushes that edge outward a little farther, but the beyond always remains. There will always be more unseen than seen, more unknown than known. As you let this thought rest with you, imagine standing at the edge of the observable universe, looking outward. Behind you lies everything we can observe: galaxies, stars, clusters, filaments, the faint afterglow of creation. Ahead lies darkness, not because nothing exists, but because light has not reached you. You stand at a horizon of vision, beyond which the universe continues, silent and unseen. It is not an ending, but an opening, a reminder that the cosmos is larger than comprehension. If the universe continues beyond what we can see, what form does it take? Is it curved like the surface of a sphere, flat like an endless plane, or something stranger still? The question of what the universe looks like on the larger scales is not just about how far it stretches or what lies beyond our cosmic horizon, but also about its shape. Not the shape of galaxies or clusters, but the geometry of space itself. When we talk about the shape of the universe, we mean something subtle and fundamental. How space is curved, whether it bends back on itself, stretches flat without end, or wraps into forms stranger than any everyday surface. This question has occupied cosmologists for over a century, because the shape of space determines not only the structure of the universe, but also its ultimate fate. To begin thinking about curvature, it helps to return to geometry. On a flat surface, the rules are simple. Parallel lines never meet. The angles of a triangle add up to 180 degrees, and the shortest distance between 2 points is a straight line. But on a curved surface, these rules change. On the surface of a sphere, for instance, parallel lines can meet at the poles, and the angles of a triangle can add up to more than 180 degrees. On a saddle-shaped surface, parallel lines diverge, and the angles of a triangle add up to less. These examples show how curvature alters geometry in ways that are subtle on small scales, but decisive on large ones. Einstein's general theory of relativity tells us that space itself can curve in response to matter and energy. Planets orbit the Sun not because they are pulled by an invisible force, but because the Sun bends space-time around it, and planets follow the curved paths. Extend this concept to the universe as a whole, and you have the possibility that space may have a global curvature, a geometry defined by its total energy content. Cosmologists describe three broad possibilities. The first is a closed universe, where space curves positively like the surface of a sphere. In such a universe, if you could travel in a straight line forever, you would eventually return to your starting point, just as a person walking across the Earth eventually circles back. The second is an open universe, where space curves negatively like a saddle, stretching outward without end. In this case, parallel lines diverge, and the universe is infinite. The third is a flat universe, where space has no global curvature, and the rules of Euclidean geometry hold on cosmic scales. Here too the universe may be infinite, but its shape is simple and unbent. The shape of space is not just an abstract question. It is determined by the density of matter and energy. Einstein's equations connect geometry to content. If the density is higher than a certain critical value, gravity dominates and the universe curves closed. If it is lower, space curves open. If it is exactly at the critical density, space is flat. Measuring the shape of the universe therefore means measuring its contents with exquisite precision. For decades, this was a central quest of cosmology. Observations of galaxies, clusters, and large-scale structure provided hints, but not enough to settle the issue. The decisive evidence came from the cosmic microwave background, the faint afterglow of the Big Bang. Tiny fluctuations in its temperature carry information about the geometry of space. In a closed universe, these fluctuations would appear larger on the sky, while in an open one, they would appear smaller. By mapping the microwave background with satellites like WMAP and Planck, cosmologists have measured the geometry to remarkable accuracy. The result? The universe is flat, or at least so close to flat that any curvature is smaller than we can detect. Flatness is a remarkable result because it suggests the universe is either infinite or so vast that any curvature is imperceptible within the observable portion. Yet flatness also raises puzzles. Why is the density of the universe so precisely balanced to the critical value? This question led to the idea of inflation, a period of rapid expansion in the earliest fraction of a second after the Big Bang. Inflation would stretch space so dramatically that any initial curvature would be smoothed out, leaving the universe flat on observable scales. It is like inflating a balloon to such a size that the curved surface appears flat to any observer looking at a small patch. Though the evidence points to flatness, we cannot rule out slight curvature. It may be that on scales far beyond our horizon, the universe bends in ways we cannot see. Or it may be that space is globally flat, infinite in extent, a plane without edges. Both possibilities are staggering, and both are consistent with what we know so far. The geometry of space remains one of those questions that is partly answered and partly open, balanced between measurement and mystery. It is worth pausing to imagine what each possibility would mean for us. In a closed universe, the cosmos is finite, though unbounded. You could, in principle, travel forever and return to where you began. In an open universe, space stretches endlessly, with no return, no looping back. In a flat universe, the simplest and seemingly most likely option, space may extend infinitely, a canvas without edges. Each shape carries a different story about what the cosmos is and how it will end. The fate of the universe is closely tied to its shape. In the old models without dark energy, a closed universe would eventually halt its expansion and collapse in a big crunch. An open or flat universe would expand forever, thinning out into emptiness. With dark energy in the picture, the story changes, because acceleration overwhelms geometry, yet the shape still matters. It tells us whether the cosmos is finite or infinite, whether space loops back on itself or stretches outward forever. As you consider this, picture yourself adrift in space, surrounded by galaxies. If the universe is closed, your journey in one direction might eventually bring you back, though the scale is so vast that such a voyage is forever out of reach. If it is open, you would travel endlessly, never repeating, never circling back. If it is flat, you might move outward forever into an infinite plane, the galaxies thinning with distance but never running out. These are not journeys we can make with ships, but with thought. They are voyages we can imagine. The shape of space is one of those questions that connects science with something deeper. It is about geometry, yes, but also about perspective. To know whether the universe is finite or infinite, whether it bends or stretches flat, is to know something about our place in the whole. It is to ask not just how things move, but how everything is stitched together. The answer may never be fully within reach, but the search itself reshapes our understanding. For as long as people have gazed at the stars, they have wondered whether our world is unique. Ancient philosophers speculated about other worlds orbiting distant suns, and modern astronomers have confirmed that planets are common throughout the galaxy. But beyond the question of other Earths lies an even deeper one. Could there be other universes? Is what we see, the galaxies, the cosmic web, the faint afterglow of the Big Bang, just one part of a much larger reality? This idea, known broadly as the multiverse, is one of the most speculative yet compelling frontiers of cosmology. It grows naturally from our theories, even if it lies beyond direct observation. The simplest version of the multiverse is an extension of what we already know about horizons. Our observable universe is limited by the speed of light and the expansion of space. Beyond our horizon, more cosmos stretches outward, unseen but real. If the universe is infinite and uniform, then there are regions so distant we will never observe them, yet they exist. Some cosmologists refer to this as the Level 1 multiverse, simply more of the same, an unending continuation of galaxies and clusters beyond our reach. In such an infinite cosmos, every possible arrangement of matter would eventually occur. Somewhere unimaginably far away, there might be another region with a Milky Way, another Earth, another you reading these very words. It sounds like science fiction, but it follows directly from the idea of infinity. A more exotic version arises from the theory of cosmic inflation. Inflation proposes that in the first fraction of a second after the Big Bang, space expanded at an extraordinary rate, smoothing and flattening the universe. In most versions of the theory, inflation never ends everywhere at once. Instead, it continues in most regions while stopping in small patches. Each patch becomes a bubble universe, like ours, while inflation continues elsewhere. This is called eternal inflation, and it produces a multiverse of bubble universes, each perhaps with different physical properties. Some may have different values of fundamental constants, different particle types, or even different numbers of dimensions. Our observable universe would be one bubble among countless others, floating in an inflating sea. There are other ways multiverses enter physics. Quantum mechanics, for instance, gives rise to the idea of many worlds. In the many worlds interpretation, every quantum event with multiple outcomes splits reality into branches. In one branch, a particle goes left. In another, it goes right. In one, you make a choice. In another, you make a different one. All branches exist, though we experience only one. If this interpretation is correct, then parallel universes exist not in distant space, but as branching realities layered atop our own. They are inaccessible, but real in a mathematical sense, as real as the one you are in now. Some string theorists propose yet another multiverse, arising from the vast landscape of possible solutions to string theory. The equations allow for a staggering number of possible vacuum states, each corresponding to a different set of physical laws. If inflation produces countless universes, each could settle into a different state, realizing different laws of physics. The multiverse would then be not just a collection of regions, but a diversity of realities, each with its own rules. What makes the idea of parallel universes so intriguing is that it emerges not from idle fantasy, but from attempts to solve real problems in physics. Inflation explains the flatness and uniformity of the cosmos, but it also leads naturally to eternal inflation. Quantum mechanics works flawlessly, but its interpretation remains puzzling, and many worlds offers a way to avoid wave function collapse. String theory seeks to unify gravity with quantum mechanics, and its landscape hints at a multitude of possible worlds. In each case, the multiverse is not an invention, but a consequence. Of course, the idea is controversial. Critics argue that because other universes may be forever inaccessible, the multiverse is not science but metaphysics. If no experiment can ever confirm their existence, can we call them real? Supporters counter that if a theory makes testable predictions and those predictions are confirmed, we must accept all its consequences, even the unobservable ones. For example, inflation makes predictions about the cosmic microwave background, and those predictions have been borne out. If eternal inflation follows, then the multiverse may be a reality, whether or not we can see it. For those of us lying under the stars, the idea of parallel universes is both dizzying and strangely comforting. It suggests that our cosmos is not the whole story, that reality is larger than we can imagine. In some universes, stars never formed. In others, galaxies cluster differently. In some, perhaps life is impossible, while in others it flourishes. We happen to live in a universe where the conditions allow stars, planets, and beings like us. The multiverse may provide an answer to the old question of why the universe is so finely tuned for life. If countless universes exist with varying properties, then it is not surprising that we find ourselves in one of the few where life is possible. Picture it for a moment. Beyond the edge of our observable bubble lies more space, more galaxies stretching outward without end. Beyond that, perhaps, lie other bubbles, each sealed from us by inflation, each with its own history. Beyond that still, perhaps, lie branches of reality, layered invisibly alongside ours, where every quantum possibility plays out. It is a vast nesting of realities, each beyond reach, yet each a logical extension of what we know. And yet, for all its grandeur, the multiverse idea also circles back to humility. We cannot see these other universes, we may never know them. They are reminders that reality is not bound by what we can touch, that our knowledge is always partial. To think of parallel universes is to accept that the cosmos is larger than comprehension, a puzzle with more pieces than we will ever fit together. As you let this thought settle, imagine yourself drifting not just through our universe, but through layers upon layers of universes, each one with its own stars, its own galaxies, its own possibilities, some similar, some strange, some lifeless, some teeming. You pass through them silently, knowing you can never enter, but still feeling their presence as a possibility. The multiverse may or may not be real, but the wonder it inspires is real enough. If expansion continues, if dark energy rules, what endings are possible? What ultimate fates await galaxies, stars, and space itself? When people first began to understand that the universe was expanding, the next natural question was what would happen to it in the long run. Expansion cannot be the whole story. Every process has a future, and the cosmos must as well. Will it expand forever, drifting into emptiness? Will it halt and collapse back inward? Will it change in some other way altogether? These questions have occupied cosmologists for decades, and while we do not yet know the final answer, we have mapped out several possibilities. Each paints a very different picture of the universe's destiny, and each adds another layer to the way we think about our place in the grand unfolding. The simplest fate is sometimes called the Big Freeze. In this scenario, the universe continues expanding indefinitely. Galaxies recede farther and farther, carried by the stretching of space. The stars burn through their fuel and fade, replaced by remnants, white dwarfs, neutron stars, black holes. Over trillions of years, even the long-lived red dwarfs will exhaust their hydrogen. With no new gas to form stars, the cosmos grows cold and dark. Black holes dominate for a time, swallowing what remains, but even they are not eternal. Through the process of Hawking radiation, they will slowly evaporate over unimaginable timescales, leaving only a thin soup of particles. The universe becomes cold, dilute and empty, expanding forever into darkness. Time itself may go on, but change ceases. It is a bleak picture, a universe that dies not in fire but in silence. Another possible ending is more violent, the Big Rip. This depends on the nature of dark energy, the mysterious force driving the acceleration of expansion. If dark energy is constant, expansion will continue but never reach catastrophic extremes. But if it grows stronger over time, if its repulsive effect increases, then eventually it could overwhelm every force in nature. First, galaxies would be torn from one another. Then stars would be pulled apart from their galaxies. Later, solar systems would be ripped apart, planets stripped from their orbits. As the end approaches, even atoms could be torn apart, their protons and neutrons separated by the accelerating expansion. In the final instant, space-time itself would rip. It is a cosmic doomsday written not in collapse but in tearing, a universe undone by the very force that once allowed it to grow. A third scenario, long considered and still possible under certain conditions, is the Big Crunch. In this picture, the expansion eventually halts and reverses. Gravity, pulling on all the mass of the universe, slows the outward rush and begins to draw everything back inward. Galaxies approach one another, then collide, then merge into a fiery cauldron of heat and light. As the collapse accelerates, temperatures rise, densities soar, and the universe returns to a state as hot and dense as its beginning. The Big Crunch is, in a sense, a mirror of the Big Bang in reverse. Whether it leads to another cycle, another expansion, is unknown, but the possibility suggests a cosmos that is not one time only but cyclical, an eternal rhythm of birth and death. Closely related to the Big Crunch is the idea of a big bounce. Here, the collapse of the universe is not the end but the beginning of another expansion. The crunch leads to a rebound, another Big Bang, another universe. This could repeat infinitely, each cycle producing new structures, new galaxies, new histories. Some theorists have explored this idea in detail, imagining a cosmos without beginning or end, only cycles. It is speculative, but it offers a vision of renewal rather than finality, a universe that dies only to be reborn. there are other possibilities as well, some stranger still. One is the heat death scenario, which overlaps with the Big Freeze but emphasizes entropy, the gradual increase of disorder. As energy spreads out evenly, no work can be done, no structures can form, and the universe reaches thermodynamic equilibrium. Another possibility is vacuum decay, suggested by certain interpretations of particle physics. If our universe exists in a false vacuum, a metastable state, it could one day tunnel into a lower energy state. This transition would expand at nearly the speed of light, destroying everything in its path. To us it would arrive without warning. It is not a fate we can prepare for, but a reminder that the universe may contain dangers written into its very fabric. Each of these scenarios, the freeze, the rip, the crunch, the bounce, the heat death, the vacuum decay, tells a different story, but all share a common theme. The universe is not eternal in its current form. It has a history, and it will have an end. The timescales are vast, stretching billions or trillions of years, far beyond human lifespans. Yet thinking about them brings perspective. Our entire history as a species, our civilizations, our struggles and triumphs, occupy only a moment compared to the cosmic timeline. The endings remind us that we live in the middle of a story, not at its beginning or end, but in a fleeting, precious chapter. It is also striking how our understanding of the universe's fate has evolved. For much of history, the cosmos was thought to be eternal and unchanging. Then the discovery of expansion revealed it had a beginning. Now we see it also has possible endings, some quiet, some catastrophic, some cyclical. The more we learn, the more dynamic the cosmos appears. It is not a static backdrop, but a living, changing entity, with birth, evolution, and eventual death. As you let these possibilities drift through your thoughts, imagine the different futures as branches of a tree. In one, the branches stretch outward endlessly, thinning into the dark. In another, they bend back toward the trunk, collapsing inward. In another still, the tree bursts, tearing itself apart from within. Each branch represents a possible path, and the universe follows one, though we do not yet know which. What we do know is that we are here, now, in a flourishing moment of stars, galaxies, and light. The endings are far away, distant enough that we can contemplate them with curiosity rather than fear. To understand the fate of the cosmos, we must also understand its foundation. What lies beneath space and time? What is the fabric that stretches, curves, and expands? When we talk about the universe expanding, about galaxies rushing apart and space itself stretching, we tend to imagine the cosmic stage as something smooth, like an invisible fabric stretching across eternity. Space feels continuous, seamless, a perfect backdrop upon which matter and energy play out their drama. But physics tells us that if we zoom in far enough, to scales much smaller than atoms, smaller even than protons and quarks, the fabric of space is not smooth at all. At those unimaginably tiny distances, it may boil and froth like the surface of a restless sea. This strange and chaotic realm is sometimes called quantum foam, and it represents one of the deepest mysteries of modern science, the structure of space-time itself. To appreciate quantum foam, we must first recall how different the universe looks at different scales. At human size, the world feels solid and predictable. Objects have positions, clocks tick steadily, and space appears flat. At the scale of planets and stars, Einstein's general relativity reveals that space-time curves, bending under the weight of mass and energy. At the scale of atoms, quantum mechanics dominates, with particles behaving like waves, positions uncertain, and outcomes governed by probabilities. But at the Planck scale, about 1035 meters, even smaller than the nucleus of an atom by a factor so extreme it defies intuition, general relativity and quantum mechanics collide. Neither theory alone can describe what happens there. It is at this scale that quantum foam is thought to emerge. Imagine trying to measure space at the Planck length. To probe such tiny distances, you would need particles of immense energy, because shorter wavelengths correspond to higher energies. But cram that much energy into such a small region, and gravity takes over. The energy density would be so high that the region collapses into a microscopic black hole. In this way, attempts to look deeper are self-defeating. The act of probing small scales creates gravitational distortions that mask what lies beneath. This interplay suggests that space-time at the Planck scale cannot be smooth. It must be fluctuating, uncertain, alive with quantum activity. Physicist John Wheeler, who coined the term quantum foam, imagined space-time at these scales as constantly bubbling with tiny distortions. Virtual particles pop in and out of existence, wormholes flicker open and shut, and the geometry of space twists chaotically. The smooth grid we imagine when we draw diagrams of space-time dissolves into froth. Distances and durations lose their meaning, replaced by quantum uncertainty. Even the concept of before and after may blur, because time itself could be subject to these fluctuations. If this sounds wild, that's because it is. Quantum foam is not something we can observe directly, at least not with current technology. It is an extrapolation, a logical consequence of combining quantum mechanics with gravity, and yet its implications ripple outward. If space-time is foamy at the smallest scales, then the universe we experience is built atop a restless foundation. The smoothness of everyday life is an illusion, a large-scale average of something deeply chaotic. Some theories of quantum gravity attempt to describe this foam in more concrete terms. Loop quantum gravity, for instance, suggests that space-time itself is quantized, built of discrete chunks or loops, like pixels on a screen. String theory offers another vision, replacing point particles with vibrating strings and suggesting extra dimensions curled up at tiny scales. In both approaches, the familiar smoothness of space emerges only when viewed from far away, much as a forest looks like a solid block of green from a distance, but up close reveals individual trees. What does this mean for the cosmos as a whole? If space-time is foamy at the smallest scales, it may influence the largest. Tiny fluctuations in the early universe, born out of quantum uncertainty, could have been stretched by inflation into the seeds of galaxies. The pattern of cosmic structure we see today, the filaments, the voids, the clusters, may trace its origin back to froth at the Planck scale. In this way, the quantum foam is not just an esoteric detail, but the birthplace of everything. There are also practical puzzles tied to the foam. One of the biggest is the cosmological constant problem. Quantum field theory predicts that the energy of the vacuum, the froth of particles popping in and out, should be enormous. But observations show that the energy driving cosmic acceleration, what we call dark energy, is far smaller, yet not zero. Why this mismatch exists is unknown. It hints that our understanding of the foam is incomplete, that some principle we have not yet grasped smooths out the chaos or cancels the energy. For a moment, let's step back and think about the scale of what we are discussing. The Planck length is so small that if an atom were blown up to the size of the observable universe, the Planck length would be about the size of a tree. It is a scale beyond imagination, and yet it may hold the key to everything. We cannot reach it with microscopes or particle accelerators, but it may reveal itself indirectly, in the behavior of black holes, in the faint background of the cosmos, or in subtle anomalies in the propagation of light. The foam may leave its fingerprints in places we can measure, even if we cannot see it directly. As you let this image settle, picture the universe not as a silent, static void, but as something alive at every level. Beneath galaxies, beneath stars, beneath atoms, beneath even quarks and electrons, space itself seethes with activity. It is like standing on the shore of an ocean that appears calm, only to discover under a microscope that every drop is filled with turbulence. The calm of the night sky is the calm of distance, Underneath, the fabric may be foaming, and so from galaxies to quantum foam, the universe reveals itself as layered, each scale hiding a different truth. To ask what lies beneath is to descend into mysteries we have not yet solved. And yet those mysteries matter, because they may determine not only the origin of the cosmos but its future. The foam at the Planck scale may connect to the fate of expansion, to the reality of dark energy, to the existence of other universes. It is the ground floor of reality, and it may be stranger than we dare to imagine. When physicists describe the quantum foam, they often picture a seething foundation where space and time themselves fluctuate, where virtual particles appear and vanish, and where geometry is unstable. To imagine that as the bedrock of our universe naturally leads to another question. If space-time is so restless, could it give rise not just to our cosmos but to others as well? Could reality itself be plural, with many universes budding off from the foam or from processes we only partly understand? This is the territory of speculation, where science brushes up against philosophy and where the boundaries of what can be tested blur into questions of imagination. One way to approach this is through inflation, the rapid expansion thought to have occurred in the first instant after the Big Bang. In many models, inflation does not end everywhere at once. Instead, it continues indefinitely in some regions, while in others it halts and allows universes to form. Each patch that stops inflating becomes a bubble, a self-contained cosmos with its own physics and history. Our observable universe would be one such bubble, while countless others continue forming elsewhere. This picture, known as eternal inflation, suggests that the foam of space-time is not just froth, but a nursery, endlessly spawning new universes. Each bubble is separate, its galaxies and stars forever cut off from ours, but all share the same underlying origin in the quantum froth. Another speculative path comes from quantum mechanics itself. In the many worlds interpretation, every quantum event produces multiple outcomes, and rather than choosing one, the universe splits into branches. In one branch, a particle spins up. In another, it spins down. In one branch, you choose one path. In another, you choose another. These branches do not interact, but they coexist, each as real as the one you perceive. If this interpretation is correct, then other realities are not far away in space, but layered alongside ours, woven invisibly into the structure of existence. The foam of quantum uncertainty is the branching of universes themselves. String theory adds yet another layer. The mathematics of strings allows for an enormous landscape of possible vacua, different ways the extra dimensions can be curled up, each leading to different laws of physics. If inflation spawns bubble universes, each may settle into a different vacuum, realizing a different version of physics. Some universes may lack stable atoms, others may lack stars, others may be entirely lifeless. The fact that we find ourselves in a universe with conditions suitable for life may not be coincidence but selection. Among countless realities, we exist in one of the rare ones where life is possible. This is known as the Anthropic Principle, and while controversial, it provides a way to understand fine-tuning without invoking design. Speculations on other realities often provoke discomfort because they push against the boundary of testability. If other universes exist but can never be observed, are they scientific objects or metaphysical ones? Cosmologists wrestle with this question. Some argue that if a theory robustly predicts other universes, and that theory is confirmed in other ways, then we must take those predictions seriously. Others caution against venturing too far into the unobservable. Yet history reminds us that horizons expand. What once seemed unreachable can sometimes, with new instruments, come into view. Perhaps traces of other realities, subtle imprints in the cosmic microwave background, echoes in gravitational waves, anomalies in fundamental constants, may one day be detectable. The line between speculation and science is not fixed but shifting. Even if evidence never comes, the contemplation of other realities has value. It stretches the imagination, reminding us that our universe is not inevitable. Its laws, its constants, its structures could have been otherwise. If other universes exist with different rules, then our cosmos is one possibility among many. To know this is to see our own existence as contingent, fragile, and precious. Life blooms here not because the universe had to be this way, but because it happened to be one of the few ways that allowed it. Philosophers have long toyed with ideas of multiple worlds. Ancient atomists imagined infinite worlds arising from the motion of atoms. Medieval thinkers speculated about other creations beyond our own. Modern science reframes these intuitions with mathematics and observation, but the core wonder is the same. Reality may be larger than the piece we inhabit. The multiverse is a new form of an old thought, dressed in equations but driven by the same curiosity. As you let this thought drift, picture the foam of space-time bubbling, each bubble swelling into a universe. Picture branches of reality splitting at every moment, each outcome playing out in its own world. Picture a vast landscape of possible laws, each realized in a different cosmos. These are not places we can visit, not destinations for rockets or probes, but possibilities we can imagine. And imagination, guided by science, is one of the tools by which we stretch toward truth. The story leads us now back to our own cosmos, to the role of time within it. If the universe expands, if realities multiply, if space itself foams, what does that mean for time? Time flows forward for us, measured in hours and days, but does it flow the same way in an expanding universe? Is time itself tied to the growth of space, to the birth and death of universes, to the froth at the foundation? Time is one of those things we take for granted in daily life. We glance at clocks. We measure our days in minutes and hours. We age by years. It feels steady, always flowing forward, the background rhythm to everything we do. Yet when we place time into the context of the universe as a whole, especially an expanding universe, it becomes far stranger than our ordinary experience suggests. To ask about the place of time in a cosmos that is stretching, accelerating, and perhaps even destined for endings like a freeze, a crunch, or a rip, is to step into deep waters. Time is not just a measure of change, it is bound up with the very fabric of space, inseparable from it, shaped by expansion and curvature. Einstein's theory of relativity reshaped how physicists think about time. Instead of being an absolute backdrop against which events unfold, time is woven together with space to form space-time. In this framework, time can flow at different rates depending on motion and gravity. A clock near a massive object ticks more slowly than one far away, a phenomenon confirmed by experiments and even accounted for in technologies like GPS. Time is not universal. It is local, relative, elastic. When we extend this idea to the cosmos, it means that time itself is linked to the expansion of space. Consider the way cosmologists describe the universe's history. They talk about the age of the universe, about 13.8 billion years. But what does that number mean? It is measured using a special kind of cosmic time, defined in relation to the expansion. Imagine a grid expanding with the universe, with galaxies carried along on the grid lines. The cosmic time is the time measured by clocks moving with that grid, unaffected by local motions. It is a kind of universal clock for the large-scale structure of the universe, though not for local systems like galaxies or black holes. This cosmic time tells us how long it has been since the Big Bang, and it is the basis for our discussions of history and destiny. Expansion itself creates a peculiar relationship with time. Because the universe is growing, light from distant galaxies takes longer to reach us than simple distance would suggest. The expansion stretches not only space but also time. When we look at light from a galaxy billions of light years away, we see it as it was billions of years ago. In this way, The sky's a time machine, showing us younger versions of galaxies, a younger universe. The farther we look, the farther back in time we see, until we reach the cosmic microwave background. The universe is a baby. Beyond that, time closes its curtain. We cannot see earlier, not because nothing existed, but because light could not travel freely. Time in an expanding universe is therefore layered. Our present moment exists alongside light from the past, reaching us now. Our horizon is not just spatial but temporal, bounded by the age of the cosmos and the transparency of space. When cosmologists trace the universe's evolution, they are mapping time as much as distance, writing a history in which galaxies are pages and photons are words. Expansion makes that history legible by stretching light into redshifts, encoding the passage of time in the spectra we measure. There is also the way time shapes the future of the cosmos. In a universe headed for a big freeze, time stretches indefinitely, but with less and less happening as energy spreads thin. In a big rip scenario, time ends abruptly in a final tearing of space-time. In a big crunch or bounce, time could be cyclical, with each universe birthing the next. In each case, time is not an endless uniform river. It has different shapes depending on the fate of the cosmos. It might be infinite, it might be finite, it might loop. Our everyday sense of time's inevitability does not capture these possibilities. The place of time is also deeply tied to entropy, the measure of disorder. The second law of thermodynamics says that entropy increases with time. This gives time its arrow, the sense of direction from past to future. In the early universe, conditions were low in entropy, hot, dense, uniform. Over billions of years, structures formed, stars ignited, galaxies assembled, and entropy rose. In the far future, entropy will reach its maximum, and time's arrow may lose its meaning. Without change, without gradients of energy, the flow of time could become irrelevant. The expansion of the universe is the backdrop to this story, stretching space and carrying entropy ever upward. Yet for all its cosmic roles, time is also profoundly personal. Our lives are measured in breaths and heartbeats, in days and seasons. We experience time not as an abstract dimension, but as memory and anticipation. What makes the universe's time so uncanny is that it is both utterly impersonal and intimately connected to our existence. We live in a cosmos where time had a beginning. The Big Bang was not just the start of matter and energy, but the birth of time itself. To ask what happened before is meaningless, because before presupposes time. In this sense, time's place is at the heart of reality. It is not a container but a participant, not a stage but an actor. The expansion of the universe also raises the question of whether time could ever end. In relativity, space-time is a manifold, a kind of shape with boundaries. The Big Bang was one boundary in the past, and the universe's fate may set another in the future. In a big rip, the manifold ends. In a big crunch, it collapses. In a big freeze, time continues but empties of meaning. Each scenario redefines time's role, reminding us that it is not eternal in the way we often assume. Some physicists speculate that time itself might be emergent, not fundamental. It could arise from deeper laws, perhaps from entanglement in quantum mechanics, or from correlations in information. In this view, time is not basic but approximate, a phenomenon that appears when systems are large enough. The expansion of the universe would then not just be a stretching of space, but a process in which time itself unfolds. This is speculative, but it highlights how unsettled our understanding of time truly is. As you consider this, imagine the universe not only as expanding in space, but unfolding in time. The galaxies drift apart but also age. Stars are born, burn and die. Light stretches, carrying memory from one moment to another. Time is the thread that connects these events, weaving them into a story. Without it, there is no history, no future, no change. Yet time itself is part of the story, not outside it. Its place is inside the cosmos, entangled with expansion, entropy, and energy. Let your mind picture a cosmic clock, not one that ticks seconds, but one that ticks epochs. Each tick marks a new era, the birth of galaxies, the ignition of stars, the acceleration of expansion. We are in one tick now, a brief one, yet one filled with awareness. Time has brought us here, to this moment, to this knowledge. The place of time in an expanding universe is both vast and immediate, both distant and close. It is the river we float upon, but also the water itself, the medium of our journey. If time is bound to expansion, if the universe has horizons and fates, where do we fit within it? What is our place in a cosmos so large, so dynamic, so restless? When people look at the night sky, it is hard not to feel small. The sheer scale of what we now know surrounds us. Billions of galaxies, each containing billions of stars, stretched across tens of billions of light years, all expanding and accelerating away. In that immensity, humanity seems almost invisible, a flicker on a pale blue planet circling one star among countless others. And yet, we are here. We can ask the questions, we can build instruments to explore the answers, and we can place ourselves, however humbly, within the infinite. To reflect on humanity's place in the cosmos is not to diminish our importance, but to recognize the strange paradox of being tiny creatures with the capacity to comprehend the vast. One way to think about our place is through scale. On Earth, we feel large enough to shape landscapes, build cities, and move oceans with dams and canals. In the solar system, however, Earth is small, one planet among 8. Its diameter a fraction of Jupiter's, its orbit a narrow band around a modest star. In the galaxy, the Sun itself is an ordinary star, one of 100 billion, orbiting the galactic center every 200 million years. In the observable universe, the Milky Way is one of billions of galaxies, an unremarkable spiral tucked into a filament of the cosmic web. The scale reduces us layer by layer until we are less than a speck. And yet the ability to step through those scales to imagine and understand them is itself extraordinary. Humanity's place is also temporal. Our species has existed for a few 100,000 years, a blink compared to the Earth's 4.5 billion years, or the universe's 13.8 billion. Civilizations rise and fall on timescales of centuries, barely perceptible against the ticking of cosmic clocks. Stars burn for billions of years, galaxies evolve for trillions. In the timeline of the universe, our presence is a brief spark. But within that spark lies consciousness, memory, imagination. We carry the awareness of time's passage, the knowledge of the past, the ability to anticipate futures. That awareness situates us uniquely as observers who know they are brief and yet seek to understand eternity. There is also the matter of perspective. When ancient people looked at the stars, they often imagined the universe centered on humanity. The Earth was thought to be at the center of everything, the heavens revolving around us. Over centuries, science has steadily displaced us. First from the center of the solar system, then from the center of the galaxy, then from the center of the universe itself. Each step has made us seem smaller, yet each has also revealed a larger truth. We are not central, but we are connected. We are made of the same elements as the stars. The carbon in our cells was forged in ancient supernovae. The hydrogen in our water dates back to the first moments after the Big Bang. To know this is to see that humanity's place in the infinite is not privileged by position, but enriched by kinship. Our place is not only about scale and connection, but also about responsibility. On the cosmic stage, our actions may seem insignificant. No empire, no city, no monument can alter the expansion of the universe or the fate of galaxies. Yet within the fragile sphere of our planet, our actions matter enormously. We shape ecosystems, change climates, and influence the future of life. In the infinite cosmos, Earth is unique to us. It is our home, our cradle, and perhaps the only place where we know life exists. Humanity's place is therefore both humble and profound, small in the cosmic sense, immense in the moral one. It is striking that, so far as we know, we are the only beings able to contemplate these questions. Perhaps there are others, scattered across galaxies, looking up at their skies with similar wonder. But we have no evidence yet. Until we do, we must recognize that we are, at least for now, the universe becoming aware of itself through human minds. Carl Sagan once said that we are a way for the cosmos to know itself, and that phrase captures something essential. Our place in the infinite is not to dominate it, but to witness it, to reflect it, to turn perception into understanding. The infinite can feel overwhelming, but it can also be grounding. When daily concerns weigh heavily, it helps to remember that we live on a small planet orbiting one star among billions, and that our worries, while real, are part of a larger story. At the same time, that larger story does not erase the value of the moment. Our lives may be brief, but they are ours. The night sky is vast, but it is also beautiful, and we can see it. The galaxies may recede, but their light still reaches us. Humanity's place in the infinite is to hold both truths at once. We are small and we are significant. There are practical ways this perspective changes us. It shapes our science, driving us to build telescopes, launch probes, and seek understanding. It shapes our philosophy, reminding us of humility and interconnection. It shapes our art, inspiring music, literature, and paintings that echo the grandeur of the sky. And it shapes our ethics, urging us to care for our fragile world and for one another, because in the infinite, we are all we have. As you reflect on this, imagine Earth as a small blue dot, floating in the black sea of space. From afar, borders vanish, conflicts disappear, only the planet remains. Around it swirl galaxies, billions of light years away, indifferent to us. Yet on that dot there are beings who wonder about the infinite, who measure redshifts, who write stories about galaxies and horizons. That is humanity's place. Not at the centre, not in control, but awake, aware, able to ask. There is a peculiar comfort in admitting that we do not know. So much of science is about measurement, precision, prediction. We pride ourselves on gathering data, reducing uncertainties, building theories that describe reality in mathematical detail. And yet, even in the most rigorous fields, there are boundaries where knowledge stops. Beyond those boundaries lies uncertainty, mystery, and sometimes silence. For many, this not knowing can feel frustrating, like an unfinished puzzle. But there is another way to see it, as poetry, as beauty. The poetry of not knowing is woven into the human relationship with the cosmos, because mystery is not an obstacle, but a companion. Think about how astronomy began. Ancient people looked at the stars and told stories. They didn't know what the lights were, and so they imagined them as gods, spirits, animals, or ancestors. These stories were not wrong in the sense of being failures. They were ways of living with mystery. Today we know that stars are nuclear furnaces, that galaxies are collections of billions of them, that the universe is expanding. But we still tell stories, not of gods and spirits, but of equations and theories. And beyond those stories, mystery remains. Dark matter, dark energy, the quantum foam, the multiverse, horizons beyond which we cannot see. The universe keeps secrets, and perhaps always will. The poetry of not knowing is in the humility it brings. To look up at the night sky and feel small is not defeat, but perspective. We are limited beings, fragile and temporary, and yet we can ask questions of the infinite. Not knowing reminds us that our knowledge is provisional, always subject to revision, always incomplete. Every time science solves one puzzle, it uncovers another, like peeling layers of an endless onion. Mystery is not a sign of failure, but a sign that there is more to learn, The cosmos is richer than our current models, deeper than our current understanding. There is also poetry in the fact that mystery keeps curiosity alive. If everything were known, if the universe were a closed book with all the answers revealed, would we still look up at the stars with wonder? It is the gaps in our knowledge that make discovery possible. It is the open questions that inspire telescopes, experiments, and late-night thoughts. Not knowing is fuel. It drives us to explore, to imagine, to test, to reach. Without it, science would wither. With it, science flourishes. Even in the things we think we understand, not knowing lurks at the edges. We know the universe is expanding, but we do not know why it accelerates. We know matter clumps into galaxies, but we do not know what most of that matter is. We know space and time curve, but we do not know how to unite that with quantum uncertainty. Our maps of the cosmos are covered with question marks, not just at the edges but in the middle, and that is not a failure. It is poetry written in the language of ignorance. The poetry of not knowing also touches something beyond science. It touches how we live. Every human life is filled with unknowns. We do not know what tomorrow brings, or what happens after death, or what our lives ultimately mean. We tell stories, build philosophies, create religions, write poems, all as ways of living with mystery. To embrace not knowing is to embrace life itself, because certainty is an illusion. The cosmos teaches this lesson at scale. It is vast, full of secrets, and we walk through it with curiosity as our light. In art, mystery is often what makes something beautiful. A painting that reveals everything at once loses its allure. A piece of music that resolves too quickly feels flat. It is the unanswered, the unresolved that gives depth. The same is true of the universe. Knowing everything would be like flattening a symphony into a single note. Not knowing is the harmony, the space between notes, the silence that makes the sound meaningful. The poetry of not knowing is the rhythm of curiosity itself. There is also a practical side to this poetry. By admitting what we do not know, we open ourselves to discovery. When astronomers first saw strange motions in galaxies, they did not dismiss them. They said, "We do not know." That gap became dark matter. When supernovae revealed unexpected acceleration, scientists did not hide the result. They said, "We do not know." That gap became dark energy. Each mystery was an invitation. Each not knowing became the seed of a new field. Without mystery, these discoveries would not exist. Not knowing can be frustrating, but it can also be freeing. It frees us from the illusion of control, from the burden of needing answers to every question. It allows us to rest in curiosity, to accept that the universe is larger than our comprehension. It invites awe, and awe is one of the most human of feelings. Awe is what we experience when we look at a starry sky or stand before an ocean or hold a newborn child. It is the recognition of something greater, something beyond explanation. Awe is the poetry of not knowing made emotional. As you let this thought settle, imagine the edge of the observable universe. Beyond it, darkness. Not because nothing exists, but because light has not reached us. That darkness is not emptiness. It is mystery. It is the place where questions dwell. The poetry of not knowing is in that horizon, in the acceptance that we cannot see beyond, yet we can still wonder. To live with that is to live with both humility and joy. And so, our journey through the cosmos brings us here, to rest not in answers, but in questions. We have travelled from galaxies to horizons, from quantum foam to the fate of the night sky. Along the way, we have seen that the unknown is not a gap to be filled once and for all, but a companion that walks with us. To embrace the poetry of not knowing is to embrace the cosmos itself. When a long day finally ends and you find yourself lying in a quiet room, there is often a moment where thoughts slow and the steady rhythm of breathing takes over. In that calm, the vastness of the universe can slip into the mind like a gentle tide. The stars we have spoken of, the galaxies receding into the dark, the mysteries of dark energy and quantum foam, all of it drifts into perspective. We are here for a brief time in a cosmos so much larger than our lives, and yet somehow it feels welcoming. This is where our reflections come to rest, not with final answers, but with peace in the immensity that surrounds us. Over the course of exploring what lies beyond the expanding universe, we have travelled far in imagination. We began with the stars close at hand, with galaxies on the run, with the fate of the night sky. We looked at horizons that limit what we can see and speculated about what lies beyond them. We asked about the shape of space itself, about the possibility of other universes, about the destinies awaiting this cosmos. Each step took us deeper, from the grand structures of galaxies down to the quantum foam at the foundation of reality. Each step revealed not just knowledge, but mystery, not just facts, but wonder. What makes these reflections calming rather than overwhelming is the perspective they bring. Our daily lives are filled with concerns, work, responsibilities, worries about the future. In the grand scheme, these are small, yet they are also real, and they matter to us. The cosmos does not erase them, but it puts them into context. Compared to galaxies stretching across billions of light years, our troubles shrink, and so does our pride. The infinite teaches humility, but also gratitude. To live in this fleeting moment, in a universe with stars and light and life, is a gift beyond measure. The vastness is not hostile, even if it is indifferent. It is silent, yes, but silence can be soothing. The stars do not ask anything of us. The galaxies do not judge. The expansion of space unfolds whether we notice or not. To rest in the vastness is to recognize that we do not need to carry the weight of everything. The universe holds it. We can let go, if only for a moment, and breathe. Imagine yourself under a clear night sky. The air is cool, the ground steady beneath you. Above, the Milky Way arcs across the heavens, its glow faint but unmistakable. Each point of light is a star, each cluster a galaxy, each faint smear a reminder of distances too great to imagine. The expansion of the universe carries them all outward, but here and now they shine for you. The vastness does not separate us, it connects us because we are part of it. The atoms in your body were born in ancient stars scattered by supernovae, carried across light years, assembled into molecules of air and water and life. To rest in the vastness is to rest in your own origins, to feel the kinship between yourself and the stars. The more we learn about the universe, the more questions we uncover. Dark matter remains hidden. Dark energy remains unexplained. Horizons block our view. Time itself may not be what it seems. The future of the cosmos is uncertain. Yet none of this lessens the beauty of the night sky. If anything, the mysteries add to it. Certainty is not required for peace. In fact, it is often the absence of certainty that makes room for awe. To close your eyes under the stars is to let the unknown cradle you, like an ocean whose depths you cannot see, but whose waves rock you gently all the same. Humanity's place in the infinite is not to conquer or control it, but to wonder at it. Wonder is enough. To wonder is to be alive, awake, aware. To wonder is to participate in the cosmos, to give it a voice through human thought. The galaxies may not notice us, but we notice them, and in that noticing there is meaning. The expansion of the universe continues, the horizons shift, the night sky evolves, and through it all we're here to see, to ask, to rest. As you let your thoughts soften, imagine drifting outward with the galaxies. They move away, carried by the stretching of space, but you are carried with them, weightless. The stars grow faint, the sky deepens, until there is only calm. In that calm, the vastness is not frightening, but soothing. It is a blanket, infinite and quiet, under which you can rest. Our reflections do not end because the universe's story does not end. but for now they pause, like a book closed at the end of a chapter, waiting to be opened again another night. What lies beyond the expanding universe remains unknown, but that is not a problem to be solved before sleep. It is a mystery to cradle, to let drift gently through your mind as you close your eyes. The vastness holds you, as it holds everything. You're small, but you belong. You're brief, but you're part of eternity. In the stillness of the cosmos, you can rest. Thank you for being here, for sharing this quiet journey through the cosmos. We began with a simple question: what lies beyond the expanding universe? And step by step, thought by thought, we followed the galaxies outward, past horizons and speculations, down into the fabric of space-time and back again to ourselves. Along the way, we found not just answers but mysteries, and perhaps a kind of peace in knowing that the mysteries remain. If you found this soothing, if you felt calm in the vastness, you're always welcome to return. Every night sky's different, every reflection unfolds in its own way, but the universe is always there, waiting quietly for us to notice. So wherever you are, whatever the time is for you, take one last breath with the stars in mind. Let the galaxies drift outward. Let your thoughts soften, and let yourself rest. You are part of the cosmos, made of its dust, carried by its light. Small, yes, but also infinite in connection. Good night, and may the vastness keep you company as you drift into sleep.